will be by Дмитро Донисюк, Богдан Савенко, Оксана Онишко, Павло Регіда, Анатолій Саченко, and Piotr Guy. Information technology for detecting hidden threats in multimedia based on a hybrid vision transformer architecture. If nobody objects, let this presentation be first. Do we have a speaker here? Pavlo, are you ready?
Yes, hello. Hello, dear colleagues. I will start my presentation. Thank you. Tell me, please, do you see the presentation?
Yes, we do. Could you open it in full screen mode, please?
Yep. Okay. Is it? Yes?
Yes, yes.
Okay, thank you. Hello, everyone. Dear colleagues, my name is Pavlo Rehida, and I will represent today the Khmelnytskyi National University. And the topic of my presentation is an information technology for detecting hidden threats in multimedia object based on hybrid vision transformer architecture. And in this work, a multimedia object is considered not only as image or video content, but as an object that passed through the web system processing mechanism and may carry the hidden impact that can be, after all, run it on your system or a network. So the presentation follow the logic of the research, and the first I will describe the motivation and evolution of the threat landscape. Then I will formulate the problem and explain the limitations of the existing approaches. After that, I will represent the objective, the threat model, and the proposed information technology. The central part of this presentation explains the hybrid architecture that will be proposed in this work, and it combines Wavelet VIT for visual analysis, Transformer XL for behavior sequence modeling, and using the attention function for feature alignment. So multimedia objects in a web system, a high level of implicit trust, usually being treated as a passive data carriers. However, adaptive generative stenography minimizes visual and statistical artifacts, while different structures can alter the object processing context. Consequently, detectors focusing solely of visual features or running behavior fail to capture threats distributed across multiple representation levels. Existing approaches have several important limitations. Neural networks are useful for logical images analysis, but their receptive field is limited. Therefore, they can suppress or lose weak high-frequency signals that are important for hidden threats detection. SRM-type statistical models in their prohibition are effective against classical hiding techniques, but they actually relies on a fixed feature space and degrade under adaptive or generative embedding. LSTM-based behavioral motoring can analyze even sequences, but it has difficulties with long sequences or system activity. Another important limitation is late fusion, when the visual and behavior branches produce independent decisions and only then aggregate them across model correlations, and this may be lost. The objective of this work is to develop and present the multimodal information technology that will help to detect hidden threats. And the contribution can be explained through the three main components. The first component is Wavelet orientation visual tokenization, which enhances high-frequency redistance and suppress semantic contact. The second component is Transformer XL behavioral encoder, which models long sequences or system events. And the third component is attention function model, which forms a shared decision space. So this slide presents the general threat model. A multimedia object is treated as an active carrier of hidden impact. Externally, it may remain formally valid or visually placeable, but during decoding, transformation, rendering, or server-side analysis, it may produce anomalous traces. The key assumption is that it is difficult for adversary to manipulate both visual structure and runtime behavior consequently without creating cross-model inconsistencies. These features are used the basis for detection. The path of this object is represented as a sequence that has input multimedia objects and the hidden impact web processing and observable traces in the visual behavior domains. The proposed information technology begins with the upload of the multimedia object. Then the object is prepared for further processing. This includes checking the format correctness and forming the internal representation of suitable for analysis. After these preparations, analysis is divided into two paths. The visual path uses VIT wavelet to detect weak high-frequency features, and the behavioral path uses TransformXL to analyze sequences of the system events generated during control and processing. The hybrid architecture consists of two encoders and multimodal fusion block. The left branch performs spatial and spectral analysis. First, a velvet transform is applied, then the low-level or frequency component is disgraced, and the high-frequency subbands are used to form tokens. After that, division transform models global dependencies between distributed features. The right branch performs dynamic analysis. It means that we will perform the monitoring module records of API calls, different memory operations, network activity, process creation, and so on. And all of these devices will be vectorized, segmented, and processed by TransformXL, which prevents context between segments. The output of both branches represent as keys and values, and the behavior description represent as query. These outputs are passed through the next attention fusion block. Okay. The logic of VIT wavelet block is to separate semantic images content from defined frequency level changes before transformer analysis. For this purpose, we use HAAR decomposition, and it's applied. It separates the visual representation into low level frequency LL, subband, and three high frequency subbands, namely that are named as HL, LH, and HH. The low-frequency component mainly contains the general shape and semantic properties in the image. Therefore, it is less informative for detecting hidden traits. Okay. The transformer, the behavioral encoder represent a system activity as an ordered sequence of the events. These events include API calls, memory operation, and so on. Standard recurrent models have limitation when processing long sequences, especially when the hidden impact is not activated immediately, but appears after several processing stages. So, and this stage TransformXL uses the segment level memory, which allows the context to be transferred between event blocks. I'm sorry. Okay. So, gated cross attention fusion. The key element of the proposed architecture is using the gated cross attention fusion. In the mechanism, visual tokens are used as a keys and values, while the behavioral description is used as a query. And as a result, the model does not only look for anomalous images regions, it also looks for visual regions that are correlated with suspicious runtime activity. The gate then parameter controls the contribution of each modality for the final decision. And here we have some kind of rule. If the hidden impact is mainly visible in the spectral visual domain, the visual branch receives the higher contribution. And if the main evidence appears during the runtime processing, the behavioral branch becomes more important. And the most significant case occurs when both branches indicate a consistent anomaly. The several data sources were used for experimental modeling. For example, it was both base 2.0 and Alaska second were used for stenographic image analysis. CFake was used for represent generative visual models that may have statistical properties close to natural images. In the multi-model settings, our one sample is represented as a pair, a spectral decomposite visual representation, and the system activity log. The architecture uses 12 VIT self attention layers, and also we used the ADAM-B optimizer and inference of the about 24 milliseconds per sample with GPU acceleration. The results show that proposed model achieved around 97.4% accuracy, 96.1% recall, and 97.2% represent precision. Compared with for example, SRNet, XUNet, and the previous SNet plus LSTM baseline, the hybrid architecture demonstrates better results across the main detection metrics. The improvement is not caused only by replacing one architecture with another. The main factor is the alignment of two different sources of evidence. If visual anomalies are weak, the behavioral branch can prove additional confirmation. Okay. The false positive rate is especially important for high-load web resources. Even a small increase of AFPR may reduce a large number of false alerts, unnecessary blocks, and legitimate multimedia objects and additional workload. So the proposed model achieved around an FPR of 0.8%. This explained by the fact that the decision is made after cross-model validation, not by a single feature source. Another important result is that under a very low payload level, specifically 0.01 BPB, the small achieved around 84% of the accuracy. Attention maps make it possible to identify the regions that contribute most to detection. Due to the different wavelet, the model shift focus from semantic objects to high-frequency residuals. From the development perspective, this technology can be used in a server-side upload inspection models and both sandbox-based processing environments, and so on. The practical value is that decision can include not only risk class, but also explanation of which visual regions and which behavioral events contributed to the final SOAR. And to conclude this work, proposed a hybrid technology for detection multimedia object. The main difference is using the cascade schemes is early interaction between visual and behavioral modalities through this attention fusion function. The experimental model showed 97% accuracy and 96.1% recall and 0.8% FPR. The approach also remains robust under low payload conditions. Okay, that's all. Thank you for your attention. I will be glad to hear any questions do you have.
Dear colleagues, maybe someone has a question to the speaker. Do not hesitate, please. Okay,
I
then
have a question,
I have
please.
one. Oh, yeah, please.
Pablo, maybe you have some ideas. How can you improve your results in future?
In the future, the next step is to use the AI models, because this approach and this architecture is using two sides of analysis of the images, and we will have to combine different information from the data carrier blocks in images that can store hidden treats, and that can be represented that is represented as system calls. So we have to get as more as possible these treats and combine into big database and try to compare them with the behavior that will occur this structure in the real-time system. So, and this will help us to create for bigger a map of the threats and influence to the system with these hidden threats.
Okay, thank you for your answer.
And I also have one question, if you may. Why is it beneficial to use a vision transformer to protect web resources from hidden threats in multimedia files? And what is the practical outcome of this approach?
So the practical result of this work is lay into using we'll try to create an effective technology that will help actually to check the multimedia files um, uh, before they're processing into the web resources and act. And visual transformer in this case is a key for achieving this result. And it remains because of two main approaches. The first one is analysis of the global context. For example, if we will compare with another classic methods, vision transformer actually allows analysis not only some local maps of the image. It also can help us to create a method that will help to analyze the complex links between different parts of this image. And this is very important, actually. And the second one is that it will help us to to find the hidden threats. Actually, this technology will help us to detect different anomaly additions into the files that are actually looks like safe to use. So in the result, I would say that file will be inspected not on the static image, but or as a potential file that can use a threat that can occur a threat to your system. Thank you.
Thank you so much for your answer. And we go to the next presentation, trying to stick to a program. So we go to the speaker number 1, Oleg Riznik, Yuri Kinash, Roman Soltysik, improvement of the synthesis method and development of a simulation model of failure-resistant coding. Is the speaker present here, Oleg?
Yes.
Great. Could you please share your presentation in a full screen mode? Yeah, thank you so much.
Okay. Good morning, dear colleagues. My name is Oleg Riznik, and I represented Lviv Polytechnical National University, Ukraine. It's my great pleasure to present our research entitled Improvement of the Synthesis met in development or simulation model of failure-resistant coding. The work introducing a novel approach to interference-resistant coding based on ideal ring bands, providing improved error detection and correction capabilities for modern common system. Slide 2, introduction. Reliable information transmission has become one of the most important challenges in modern digital communication. Communication channels are continuous affected by noise, interference, fading, and summiting even intentional attacks. Therefore, the development of efficient error correcting coding methods remains an important scientific and practical problem. The main objective of our research was to develop a coding technique that combined high real with relatively low computational complexity. Next slide, 3. Many well-known coding techniques have been proposed over the last decades. Among the most popular solutions are BCH codes, Reed-Solomon codes, Hammond codes, several scenarios approach. Also, this method demonstrates excellent performance. Many of them requires complex decoding algorithms or introduce significant reductions. Our research proposes an alternative solution based on the mathematical properties of ideal ring bands. Slide number 4, proposed method. The proposed coding method is based on algebraic combinatorial structure called the ideal ring bands. Its mathematical properties granted an equal representation of every information symbol. Using the properties, we generate non-equidistant code words that signify improve the ability of information transmission. One of the main advantages of the proposed method it is ability to construct highly robust consequence while making efficient implementation. Next slide 4, coding principle. The encoding procedure begins by selecting the corresponding information symbol. Each symbol is converted into binary code word generated according to the selected ideal ring bundles. If the symbol directly correspondent to one bundle element, the appropriate button is activated. Otherwise, the code word is constructed by combining several bundle elements according to predefined combinatorial rules. Okay, next slide, coding example. The slide illustrates the complex encoding procedure. The selected alphabet contains 11 symbols. Each symbol receives its own encoded binary representation. The original message is converted into a binary sequence suitable for reliable transmission through a noisy communication channel. Next slide 7, simulation method. To verify the proposed method, we developed a comprehensive simulation method. The software performs encoding transmission through a
Все, давай. Добре.
noisy channel decoding and error analysis. Different communication scenarios were investigated, including random errors and international interference. The simulation confirmed stable operation under various channel solution. And experimental result. Experimental evolution demonstrate very promising result despite relatively high reductions. The proposed coding method provides excellent protection against transmission error. The obtained result confirms that the proposed method significantly improves communication reliability. And next slide, conclusion. In conclusion, we have proposed an improved synthesis method based on ideal ring bundles. The proposed approach introducing a new model for construction non-existent error-correcting codecs. One method is capable of detecting up to 50% of transmission error and corrected up to 25% of error within a code block. The characteristic make the proposed coding technique effective for reliable communication system, embedded device, secure information storage, and industrial application. Future research with focus in optimization decoding algorithms and implementing the proposed method on FPGA and other embedded hardware purpose. Thank you for much for attention. I especially appreciate your interest in our research. Thank you.
Thank you so much for the presentation, dear colleagues. Any questions, please? Any questions? Dear colleagues, be active, please, and participate in the discussion. Could you please tell us, your presentation is called Improvement of the Synthesis Method and Development of a Simulation Model. Did you measure the numerical evaluation of your improvement? Maybe it is the percentage, or in which scale, in which value did you improve the synthesis method? Maybe you have it on the slide.
And change method for synthesis noise-resistant code sequence has been proposed through the use of ideal ring bundles by experiment emulation model. This method improves the robustness to the received sequence, enables the detection of up to 50% and the correction of up to 25% of distorted symbol across the length of the noise-resistant count up sequence.
Thank you so much.
Simulation model for noise-resistant coding based on non-uniform combinatorial configuration has been implemented of the C++ programming language.
Thank you so much for a broad answer, and we go to the next presentation by Ярослав Гладкий, Мирослава Гладка, Володимир Дружинін, Ірина Борисенко, and Sergey Pali, hardware configuration space of an intelligent information technology for rehabilitation support. Do we have a speaker here? If there is no speaker for this presentation, then we go to the next one by Вячеслав Репета, Богдан Дурняк, Юрій Кукура, Олена Гаврилишин, Павло Ривак, and Abdel Podek and Salem, models of an intelligent image transformation system for cyanotype reproduction. Do we have speaker here?
Yes.
Great. Could you please share your presentation?
One moment, please. Can you see my presentation?
Yes, but not in a full screen mode. Could you please open it in the full screen?
Maybe I try again.
Okay.
And now?
Now, yes.
Yes, that's okay. Okay, thank you. Dear colleagues, I am pleased to present our paper entitled Models and Intelligent Image Transformation System for Cyanotype Reproduction. The study is devoted to the development of the intelligent tone transformation model for preparing digital negatives suitable for cyanotype photographic reproduction. Cyanotype is one of the oldest alternative photographic processes. It is based on the ability of the iron salts to form blue water insoluble compounds under ultraviolet radiation. Today, cyanotype is used not only for historical photographic technique, but also in artistic, educational, and experimental printing processes. The relevance of this research is determined by the fact that the modern cyanotype was evolved from the purely analog processes into hybrid digital analog workflow. At the first stage, the image is prepared digitally. Then the digital negative is printed on the transparent film. Finally, the negative is used for contrast exposure on the photosensitive cyanotype layer. The digital negative is decides influence on the tonal range, contrast, and detail reproduction on the final print. However, standard graphic editors such as Adobe Photoshop and similar tools do not directly take into account the photochemical specificity of the cyanotype reproduction. Tone correction is usually performed manually, so the results depend strongly on the operator's experience, and it is not always stable and reproducible. Therefore, is need for formalized and intelligent approach to constructing the tone curve of the digital negative. The main problem is that cyanotype has a nonlinear tonal response and a relatively high contrast. To obtain a full tone range of the final print, the digital negative must provide sufficient opal density and areas corresponding to the highlights of the original image while preserving details in the shadow regions. In the traditional approach, the user may rarely adjust curves, contrast, brightness, or levels. However, such correction does not guarantee stable results for different images. For this reason, the present study proposes transition from the intuitive manual editing to an analytically defined tone model whose parameters can adapt it to the statistical characteristic of particular image. The aim of the scientific idea of the study is to develop the intelligent tone transformation model for automated preparation for digital negatives for cyanotype reproduction. The main idea is to use a modified sigmoid function that allows independent controls of shadows, highlights, and the balance of the tone curve. Unlike manual adjustment in the graphic editors, our proposed model defines the tone transformation mathematically. The The model is based on the sigmoid transformation of the normalized image brightness. As the positive tone response is obtained, tone inversion it is performed. As a result, a digital negative is generated for printing on transparent film and subsequent exposure for cyanotype exposition. An important feature of the proposed model is that the parameters have a clear technological interpretation. The parameter gamma controls behavior of the curve of the shadow regions. The parameter beta controls the highlight regions. The parameter K shifts the operation point of the curve and determines the balance between shadows and highlights. Thus, the model does not merely exchange a contrast. It controls the tonal structure of the negative in accordance with the requirements of the photochemical reproduction processes. The practical implementation of the model was carried out in the MATLAB Simulink environment. The system includes several main blocks. Can you see? You can see it on this slide. The first block is a parameter selector. It analyzes the global statistical characteristic of the image and determines the parameters of the sigmoid function. The second block is a tone engine. It implants the generate sigmoid function using the adaptive parameters gamma, beta, and k. The third part of the model is related to the local contrast analysis. For this purpose, the derivative of the tone curve is used. It shows in which regions of the tonal range the system is more sensitive for brightness changes. The decision-making process based on the global image characteristics, min L is average brightness, STDL standard division of brightness, p-shadow proportion of the shadow pixels, and p-highlight proportion of the highlight pixels. The study also uses a compact regression neural network with a single hidden layer. Its role is not high-capacity learning, but rather the demonstration of an interpretable mechanism of the mapping image features for tone curve parameters. The complete transformation can be represented as image features, tone curve parameters, and digital negatives as step by step. This means that the curve parameters are not selected manually. They are informed from the structure in the input image. Yes. The paper presents an example of the digital image transformation. The first, the color image, is converted into grayscale, and then the adaptive sigmoid transformation is applied. After that, tone inversion is performed and digital negative is generalized. This parameter configuration moderately exchanges shadows details and strongly compresses the highlight regions of the negative. This is important for controlling ultraviolet light transmission during cyanotype exposure. The histogram results are confirmed by the histogram analysis. The transformation results, I'm sorry. The histogram of the original image shows that mole pixels intensities are concentrated in the mid-highlight region of the tonal scale. You can see on the slide. This means that the image contains many light and mid-light areas. It's after sigmoid transformation, the envision the brightness distribution changes significantly. A large part of the bright values of the original image is transferred to the dark region of the negative. This creates high optical density in the corresponding areas and of the negative and reduces ultraviolet transmission. Thus, the model provides not only image inversion, but also controlled tonal redistribution according to the requirements of the cyanotype reproduction. To evaluate the behavior of the tone curve, local contrast is used. It is defined as a derivative. This function shows how strongly the output brightness changes is response to changes in the input brightness. Therefore, the local contrast curve explains the logic of intelligent digital negative formation. And conclusions. The study substantiates feasibility of using model sigmoid tone transformation for preparing digital negatives in cyanotype processes. The proposed model allows independent control of shadows, highlights, and tone curve balance. The intelligent block based on the global statistical image features formalize the decision-making processes that is usually performed intuitively in alternative photographic practice. The analysis of the image histograms and local contrast confirms that the model provides controlled darkening, highlight areas in the negative, preservation of the shadow details, and more stable distribution of contrast. The obtained results create prerequisites for improving all the repeatability, stability, and quality of the cyanotype prints. In the future, this approach can be used not only for cyanotype, but also for other alternative photographic processes. Thank you for your attention. Maybe you have any questions, please.
Dear colleagues, your questions, please. Then I have one. Could you tell us how does the system preserve the visual characteristics of cyanotype?
Years ago, this process is did it by intuitively of the operator, and now we propose a new way for preparing the image, and this way is that the model independent controls of shadows, highlights, and we use for this control tone curve balance. And this intelligent block based on the global statistical image features formalized the decision-making process that's usually performed rather intuitively. And now it is based on the mathematical process.
Thank you so much. Dear colleagues, more questions? Thank you so much for your presentation, and we go to our next speaker. The next presentation is by Maria Yukhomchuk, Vyacheslav Kovtun, Vladislav Losko, and Yuri Ivanov, secondary similarity criteria in intelligent information technologies for optimal system control. Do we have a speaker here?
Yes, good morning.
Good morning.
Is the presentation on screen?
Yes.
Okay. Respected colleagues and guests, today I have the honor to present the paper titled Secondary Similarity Criteria in Intelligent Information Technologies for Optimal System Control, authored by Maria Yukhomchuk, Vyacheslav Kovtun, Vladislav Losko, and Yuri Ivanov. From Vinnytsia National Technical University, I am Yuri Ivanov, the speaker of this work. The rapid advancement of intelligent information technologies creates a strong demand for effective methods of analysis, modeling, and optimal control of complex technical systems. This is especially relevant for adaptive control, digital twins, and decision support systems, where the correct interpretation of system state parameters is critical. Secondary similarity criteria play a central role here. They establish stable relationship between the components of the objective functions and constraints in optimization problems. In this work, we treat them not as pure mathematics, but as informative features that integrate heterogeneous data, reduce dimensionality, and reveal invariance even in non-linear and uncertain environments. In recent years, the concept of similarity has been actively studied. For example, Wong and Meng proposed data-driven behavioral similarity frameworks for heterogeneous systems. Other works introduced gamma-delta similarity for non-deterministic linear systems and Pythagorean fuzzy similarity measures for tuning controllers under uncertainty. Digital twins research emphasizes similarity metrics for model validation, synchronization between physical and virtual objects, and online validation in manufacturing and energy systems. Similarity indicators have also been successfully applied to optimization, alarm detection, case-based reasoning, and direct transfer of optimized controllers using dimensionless model predictive control. Nevertheless, most existing approaches focus on narrow applications, and this paper fills an important gap by offering a unified, structurally grounded framework for secondary similarity criteria that are interpretable, invariant, and naturally integrable into modern intelligent control system. Let us look at the core mathematical formulations. The optimal control problem in intelligent technologies is stated as minimizing a general technical economic indicator given by the polynomial formula 4.1 and subject to the constraints formula 4.2. Within the framework of intelligent systems, every term of the objective function and every constraint is considered a separate information component. The similarity criteria obtained by normalizing these terms act as weight coefficients, clearly showing the significance of each factor of the optimal decision-making process. Optimal similarity criteria are obtained from orthogonality and normalization conditions using the exponent matrix. Secondary criteria are simply ratios of primary ones. In many practical cases, when a variable appears in only two terms, this ratio depends only on the exponents, not on coefficients. This makes secondary criteria invariant and stable under parameter changes. They serve as compact information features of the optimal state and work for both canonical and uncertain or non-canonical models, which is essential for real-world intelligent control systems. We also introduced similarity indicators defined in scaled relative units for control parameters U. The indicators takes a special form that allows establishing parametric similarity between the real object and its modern digital model. When such similarity exists, corresponding algebraic components must be equal. These indicators are particularly valuable for intelligent control systems with reference model and digital twins, as they enable automatic scaling and adjustment of control actions.
Excuse me, sorry to interrupt you, but you showed us not the presentation, but the notes to the presentation.
I don't understand. The presentation is not on the screen?
The presentation was not visible. You switched the screen to the notes, to the Microsoft Word document. Now there is a presentation.
Okay,
Yes.
okay.
Yes.
Okay. 7. To make this approach practical, we propose a clear modular algorithm. It includes 6 main stages: formulation of the optimal model, definition of similarity criteria, analysis of dimensional matrix and computation of secondary criteria, interpretation of this criteria as information features, integration into intelligence control or decision support algorithm, adjustment digital model parameters using similarity indicators. This structured algorithm ensures flexibility and can be adapted to different classes of technical objects. One of the most important practical advantages is that secondary similarity criteria depends mainly on the exponents of the system variables. This allows computing them before solving the full optimization problem, enable early qualitative analysis and model simplification. These criteria give a static view of the optimal point, while indicators provide dynamic adjustment capabilities. Together, they form an effective two-tiers strategy, ideal for digital twins. This enhance robustness via interpretable invariants, outperforming many data-driven methods. We have shown that secondary similarity criteria serve as powerful informative features. They reduce optimization dimensionality, increase control stability, and ensure reliable parametric coordination in digital twins. This approach is promising for energy systems, electrical networks, cyber-physical objects and systems. Future work includes experimental validation and extension to multi-agent distributed systems. Thank you for your attention.
Thank you for the presentation, dear colleagues. Do you have any questions to the speaker? Then I have a question. Tell me, please, did you consider the ways of improvement, the drawbacks of your system, if any?
We works only as with secondary criteria as can be computed before solving optimization problems, enable preliminary qualitative analysis, identification dominant components, model simplification, and we proposed a framework provides a unified, interpretable foundation for synthesis, optimal and adaptive control strategies in intelligent information systems.
Thank you. Dear colleagues, more questions, please? If no, then we go to the next speaker.
Thank you.
The next presentation is by Natalia Pytliak, Yuri Klots, Dmytro Tomashchuk, Mykolai Karpinsky, Maria Stadnik, and Artem Boyarchuk, Adaptive Fuzzy Model for Anomaly Detection in IoT Network Traffic. Do we have a speaker here?
Yes. Please stop, Sarah.
Couldn't please, the previous presenter, could you please stop sharing the screen? Yeah, thank you.
Thank you. Do you see my presentation?
Yes.
Good morning, dear colleagues. My name is Yuri Klots. This research is devoted to anomaly detection in Internet of Things network. The Internet of Things is developing very fast. More and more devices are connected to networks. These devices generate large amount of traffic at the same time. Many IoT devices have limited resources. They often have weak protection and rare security updates. Because of this, IoT networks are very vulnerable to to attack. So anomaly detection in IoT traffic is an important task. There are several problems in this area. IoT traffic is heterogeneous and dynamic. A traditional signature-based system cannot detect new attacks well. They work only with known patterns. Deep learning methods can give good results, but they often need large datasets and powerful computer. Also, many models are difficult to explain. For this reason, we need an adaptive, lightweight, and understandable method. The aim of this work is to develop an adaptive fuzzy model. The model is used for anomaly detection in IoT network traffic. The model forms linguistic terms automatically. It generates fuzzy rules automatically. It uses Suggestion type fuzzy interface. It can also adapt online. This means what full retraining is not needed then traffic changes. The scientific contribution is the combination of several methods is one model. First, we use fuzzy C-means. It helps to form a membership function automatically. Second, we use the Van-der-Mendel algorithm. It generates fuzzy rules from data. Third, they use Suggestion type fuzzy inference. It calculates the anomalous score. Finally, we add the ruler gain agent mechanism. This mechanism removes all of weak rulers. And result, the model can adapt to changes in traffic. This slide shows how linguistic terms and membership functions are formatted. At the beginning, the model receives traffic future values, then the fuzzy C-means algorithm groups these values into fuzzy clusters. Each cluster is interpreted as a linguistic term. For example, the terms can be normal, suspicious, anomalous, and or critical. The model uses 5 terms for each input variable. This helps to describe traffic states step by step. The main advantage is that thresholds are not set manually. They are formatted automatically from data. This slide shows the process of fuzzy rule generation. The Van-Mendel algorithm works with training samples. First input values and fuzzy fit. Then the algorithm forms the if-then rules. For example, if packet rates is high and flow duration is short, then traffic can be anomalous. Each ruler receives a weight. If several rulers have the same conditions but different conclusions, the model keeps the strongest ruler. So the final ruler base becomes compact and clear. This slide shows the general structure of proposed system. The system has 2 main stages. The first stage is offline training. At this stage, the model proposes datasets. It extracts traffic features, then it forms linguistic variables and fuzzy rulers. The second stage is online detection, and at this stage, new IoT traffic is analyzed in real time. The model calculates an anomaly score. If the score is higher than the threshold, the traffic is classified as anomalous. The system also updates rules and terms during operation. This allowed the model to work with changing traffic. The model was tested on these OpenIoT traffic datasets. These datasets are MQTT set, IoT ID 20, and CIC IoT 2023. They include different types of attack. For example, DOS, DDoS, Mirai, scanning, brute force, and spoofing attack. The experiment used 70 by 30 train test split. The decision of threshold was 0.6. The sliding window size was 100 records. The adaptation interval was 50 windows. The result high of all datasets. For MQTT test, the accuracy was above 98%. For IOTA ID20, the accuracy was also above 99%. For CIC IOT 2023, the accuracy was also above 99%. The F1 scope was also higher than 98% for all datasets. This result shows that the model works well on different IOTA traffic data. To conclude, the proposed adaptive fuzzy model provides high detection quality. It's also interpretable and computationality efficient. The model avoids manual threshold settings. It can adapt to traffic changes without full retraining. This is important for a real IoT network. The model is suitable for participant security monitoring. It can be used to environments with limited computing resources. Thank you for your attention.
Thank you so much for the presentation. Dear colleagues, do you have any questions to this presentation? I have one question. Could you please answer why was the decision threshold of 0.6 used, and how can changing this threshold affect the number of false positives?
Thank you for your question. The threshold of 0.6 is used to classify traffic as normal or anomalous. If the threshold is decreased, the model may detect more attacks, but the number of false positives may increase. If the threshold is increased, they may be false positive, but some attacks may be missed.
Thank you so much for the answer. If there are no other questions, then we go to the next presentation. Thank you so much. The next presentation is by Igor Lyakh, Igor Tverdohlyb, Taras Dechko, and Roman Kuruca. Modified VLAS with dynamic channel allocation to prevent behavioral analysis. Do we have a speaker here? I think no. The next presentation is by Denis Volkov and Vera Lyubchenko, Topology and Evidence-Aware Risk Assessment for a Microservice-Based System. Is there a speaker? Also no. And we go to the next presentation by Vyacheslav Kovtun, Artem Guralnik, Lyudmila Husak, Oleg Kovalyuk, Risk-Sensitive Decision-Making in Security Operations Center, Alert Escalation Under Resource Constraints. Is there a speaker? Vyacheslav, are you ready to present? Vyacheslav, are you ready?
I'm sorry, I have some. Do you hear me? Do you hear me?
Yes, we do.
I'm sorry, I have some problems with presentation. If it possible, can I present my presentation in the next site of the conference? I hope that till that time I will solve my problems. Is it possible?
I think we need to ask the my colleague organizer, but we have other issue that not all the speakers are present here. We don't have the speakers of the presentation number 2, number 6, and number 7.
Yes, I saw. That's why I hope that I will solve my problems in till that time that those people presented their works, but they are not present here. So once more time, or I can try
Yes,
to
but
present my.
I understand. But if there are no more speakers, then we have to start the next section earlier. I think it is possible for you to present a little bit later, but uh, since we don't have speakers of 3 presentations here, uh, I think I give the floor to my colleague with the second section that was supposed to start at 12. Or we can have a break.
Okay,
Sergey,
so
are you here?
Yes, I'm here.
What should
So,
what
what
should
the
what
problem
should we
do we
do?
have?
We have 3 speakers who are not present currently. The speaker of the presentation number 2, number 6, and number 7. There are no speakers in here in the waiting room, and we have the problem with the presentation, with the last presentation. Vyacheslav Kovtun asked to present at the next section.
Well, okay, so we in this case we can do next way. I suppose that we have to wait, for example, for let's say 7 minutes, and if there will be no participants, we will make some coffee break.
Okay, and for Vyacheslav, is it possible to transfer the speech number 9 to the next section for speakers to get ready? Yeah, okay, Vyacheslav, you will be the first at the next section, and we are waiting for the rest of participants for 7 minutes. And then at 10:20, I suppose, we either give them the word, or we have the coffee break till the next section. Yes?
Yeah, sure.
Thank you for understanding.
So we are waiting for the speakers.
Okay, Olha, please let me know the name of a participant who are absent, and
yes, sure.
And
Sure.
I'll try to connect with them.
Thank you. Dear colleagues, since we don't have the speakers here, nobody joined us, then we have a coffee break, I think, for 10 minutes. And after that, we start the next section. If the speakers of the first section join us, then they will have the floor, the opportunity to present. Sergey, do we need to have a coffee break, or we can start the next section right now?
Let's continue right now, of course.
Okay. If the speakers are ready, then we can continue.
Who will be presenting, Vitaly or Vitaly? Yeah?
Good afternoon. I'm ready to present. Can you see my screen?
Yes, we can.
Okay. Good afternoon. I am Vitaly Alexeiko, and I am a PhD student. Today, I want to present a paper, Spatio-Temporal Deep Learning for Joint Forecasting of Distributed Renewable Generation and Electricity Demand under Uncertainty. The authors of the study, Tatiana Hovorushchenko, Vitaly Alexeiko, Jan Rabchan, Olha Tamaniuk, and Abdel Badih Salem. We represent Khmelnytsky National University from Ukraine, University of Zhilina, Slovakia, and Ain Shams University, Egypt. Global decarbonization and mass integration of distributed renewable energy create a level of topological, meteorological, and stochastic complexity that traditional statistical tools and basic machine learning algorithms are fundamentally unable to cope with proper operational reliability. The global energy paradigm is undergoing an unprecedented transformation driven by the imperative of decarbonization and the transition to sustainable energy sources. Modern energy systems are evolving from a traditional centralized model based on fossil fuels with predictable generation levels to decentralized smart grids. These new grids are characterized by a high level of penetration of distributed renewable energy sources, such as solar photovoltaic plants and wind turbines integrated directly at the consumer or distribution network level. This transition, despite its environmental feasibility, introduces a colossal level of stochasticity, volatility, and nonlinear dynamics into the processes of balancing and managing the electricity grid. Unlike traditional generation, energy production from renewable sources is deeply weather-dependent, intermittent, and extremely difficult to directly control. This fundamentally disrupts the classical dispatch paradigm where generation flexibility adapted to a relatively predictable demand schedule. Despite the proven high accuracy of point forecasts based on deep spatio-temporal learning, they provide the system dispatcher or control algorithm with only a single expected average value of generation or demand. This approach is fundamentally dangerous because it completely ignores the statistical probability of deviations. In the new paradigm of smart grids with a high proportion of stochastic and unstable renewable sources, making decisions based only on point forecasts makes the power system strategically vulnerable to extreme events. Energy management requires an inevitable transition to probabilistic forecasting. Instead of a single number, the model should provide a complete continuous probability distribution of future system states, or at least prediction intervals with an operator-specified confidence level, for example, 90%, 95%, or even 99%. To provide reliable uncertainty quantification, modern deep learning models must correctly model and separate two fundamentally different types of uncertainty. First of all, aleatoric uncertainty is also known as data uncertainty. This is the objective inherent noise in the observation data itself. It is caused by measurement errors, inaccuracies in the input numerical weather predictions, also known as NVP, or the natural stochasticity and randomness of wind flows at the micro level. An important feature of aleatoric uncertainty is that it cannot be reduced even if an infinite amount of training data is collected. And the second one is epistemic uncertainty, is also known as model uncertainty. This is the subjective uncertainty that arises from the lack of knowledge of the neural network itself. It can be a consequence of insufficient or unbalanced representativeness of the training sample. For example, the model has never seen data on the behavior of solar panels during a powerful dust storm or a Category 1 hurricane, or due to an incorrect choice of the network architecture itself, insufficient depth or capacity. Unlike aleatory uncertainty, epistemic uncertainty systematically decreases as more quality training data is accumulated. To predict the values of the time series, a number of models were selected, both classical machine learning models such as ridge regression, random forest, gradient boosting machine, and deep learning methods, in particular multilayer perceptron, long short-term memory, transformer, and spatio-temporal graph neural network. And in renewable energy forecasting, deep learning models face extreme data volatility due to changing weather conditions. Evaluating these models requires two levels of evaluation: accuracy, which measures how close the forecast is to the actual value, and a quantitative assessment of uncertainty, which measures how reliable and precise the forecast boundaries are. When implementing uncertainty quantification in a spatio-temporal deep learning model, several mathematical methodologies are used, each of which offers its own trade-off between the quality of uncertainty estimation and the cost of computational resources. The comparative analysis revealed that deep ensemble methods and Monte Carlo dropout typically demonstrate the best calibration of results and the most accurate assessment of epistemic uncertainty among all models. At the same time, despite the mathematical elegance of Bayesian neural networks, their development in real-world energy management environments is often limited by the problem of variance shrinkage or mode collapse in complex spatio-temporal data, where traditional quantile regression, despite ignoring the epistemic part, gives particularly more useful results. The quantile regression metrics demonstrate the model's failure. The coefficient of determination indicates that the model performs worse than the constant mean predictor. The gradient boosting machine-based quantile regression independently fits the individual quantile functions, resulting in overlapping intervals and unstable medians on this dataset. The extreme pi-i-CP value confirms the overlay wide intervals, which is a classic sign of underfitted quantile models where the intervals do not adapt to the structure of local variance. The Bayesian neural network exhibits significant undercoverage, and pi-i-CP metric versus the nominal 90% represents something like 38% coverage gap, which is a critical failure for any security-related deployment. The posterior variance of the Bayesian neural networks is severely underestimated, and this pathology is consistent with a posterior collapse in the variational mean field inference, where the approximate posterior moves towards the prior faster than the probability can expand it. The Bayesian neural networks is overconfident by a factor of about 3. The Monte Carlo dropout shows partial calibration recovery And the Monte Carlo dropout recovers a significantly larger posterior uncertainty than the Bayesian neural networks, but remains miscalibrated. The dropout coefficient 0.2 acts as a fixed epistemic prior. It does not adapt to heterostatic aleatory noise in the data. An example is near zero energy at night versus highly disparate solar generation at noon. The deep ensembles show the best accuracy. The metric R-squared is near 90% and the lowest RMCE. However, PI-ICP is about 22% gap, which is surprisingly low for a member ensemble. The variance of the member differences intermodal variance is insufficient to capture the full forecast uncertainty on this dataset. Conformal forecasting is the only method that achieves a nominal coverage of 90% with a theoretical guaranteed coverage factor under the assumption of interchangeability. This is a defining property of conformal forecasting. That is, it is the only method with a finite sample validity guarantee rather than an asymptotic one. The price is the interval width of 575 watts, which is wider than in ensembles and Monte Carlo dropout because the split conformal procedure uses a single global quantile of the discrepancy estimate rather than the input conditional width. Among the high-performance models, MLP and STGNN achieve the narrowest prediction intervals. STGNN exhibits excellent UQ optimization. It achieves identical coverage probabilities to random forest and GBM, but does so with a significantly narrower interval width. This indicates that the spatio-temporal structure creates sharper, more reasonable uncertainty bounds without compromising empirical coverage. However, the need for significant computational resources and long training time make it inefficient. Thus, multilayer perceptron becomes the best solution among the considered models. The analysis demonstrates that the combination of deep learning methods, in particular the multilayer perceptron architecture and modern methods of quantitative uncertainty assessment, such as conformal analysis, forms the most mathematically advanced and engineering-based technical basis for the operational management of future smart grids. The transition from classical deterministic isolated forecasting to multidimensional probabilistic prediction changed the very philosophy of power grid management because instead of constantly reactively responding to sudden frequency or voltage imbalances, system operators receive a powerful tool for predictive optimization of reserves based on clearly quantified risk intervals. At the same time, the practical widespread deployment of these intelligent systems is hindered by several real-world engineering barriers, including the unstable quality of sensor telemetry, growing cybersecurity threats, such as data integrity attacks, and the extremely high computational cost of deep mathematical models. Effectively solving these problems requires a comprehensive approach and synergy of various branches of computer science, in particular the use of neural networks themselves for continuous self-healing and data cleaning in real time, as well as the active transfer of lightweight, quantized forecasting algorithms directly to the edge computing level. The successful implementation of the proposed spatio-temporal methodology has the potential not only to significantly reduce operators' financial losses associated with operational errors and the maintenance of excessive reserve capacity, but also to provide a viable pathway towards a reliable, resilient, and economically sustainable operation of future energy systems with near-complete integration of renewable energy sources. In this context, artificial intelligence evolves beyond a conventional analytical tool, becoming a fundamental component of next-generation energy infrastructure. Thank you for your attention. Maybe you have some questions.
Thank you, Vitalik. Dear colleagues, does somebody has any questions? Okay, Vitalik, what is the main drawbacks and limitations of your research, which are to be improved?
Yes, the most valuable limitation, as for me, it's some problems with data collection and with telemetry. So we cannot validate our model in real data or near real data, and we rely only on the data sets. And the most of these data sets are synthetically generated using fuzzy logic or other methodologies of synthetic generations, but we cannot now rely on telemetry, and this is a scope of our further researches because we want to test and validate this model using telemetry and data real collected from some energy grids.
Okay, thank you. Dear colleagues, more questions? No? Okay, thank you. So the next speaker will be Olha. Yes, your team.
Thank you so much. Let me share my screen with the presentation. Can you see the presentation?
Yes, we can.
Okay, thank you, dear colleagues. Good morning to everyone. Let me present the topic, information system for automated static balancing of rotating parts in the CAD environment, prepared by the team of Anatoly Gordeev, Viktor Gorokhovsky, Nazar Kostyuk, and Huda El-Bouhisi. And today I will be presenting this work. Static imbalance is a common engineering problem. Even a small shift of the center of mass from the rotation axis can cause vibration, increased mechanical wear, noise, and reduced reliability. Traditionally, balancing is performed manually during design or experimentally after manufacturing, which is both time-consuming and prone to human error. To address this problem, we developed an automated CAD integrated system balanced on the SolidWorks API. The system automatically detects imbalance, calculates the required counterweight, generates the necessary geometry, and verifies the result without manual intervention. The architecture of the proposed system consists of three main layers. The data acquisition layer extracts mass properties and geometric information from the CAD model. The computation layer calculates the imbalance and determines the required counterweight parameters. And finally, the geometry synthesis and validation layer automatically creates the balancing geometry and repeats the calculations until the required accuracy is achieved. The balancing algorithm minimizes the offset of the center of mass relative to the rotation axis. It calculates the counterweight mass, places within the available design, and rebuilds the CAD model and repeats the process until the balancing tolerance is satisfied. In practice, convergence is usually achieved within only 2 or 3 iterations. Here we have the modular architecture of our information system, which consists of 5 modules. Here we can see the input and output data of these models, and the chart is presented on the slide. And here is the algorithmic implementation of the proposed approach. The here we have the steps of the algorithm and the algorithmic implementation, where we have the properties. The algorithm properties include deterministic convergence under static balancing assumptions, full integration with CAD-MAS property calculations, independence from external simulation environments, iterative tolerance-based stopping criterion, and extendable to multiplane or dynamic balancing. We validated the proposed approach, and we used the intentionally unbalanced crankshaft model in SolidWorks program. And here we have the computational complexity analysis that is usually calculated during the measurements. And here is the chart of the automated workflow. We have 4 steps that we need to do. It's to load the model, to extract math, generate weights, and verify and export. The key distinction from traditional practice lies in transferring balancing from manual and experimental stages to a fully automated CAD integrated computational process. The balanced model transfers directly to downstream CAE or CAM processes without separate experimental correction stages. And also we validated it on purpose with the unbalanced crankshaft model. The automated system computed counterweights parameters, generated parametric 3D geometry, and iteratively recalculated mass properties until the predefined tolerance was satisfied. The performance was compared against traditional manual balancing, and we can see that the automated system reduced balancing time by approximately 93%, improved center of mass accuracy by 98%, and significantly reduced design errors while providing fully repeatable results. In conclusion, the proposed system demonstrated that static balancing can be transferred from manual and experimental procedures to a fully automated digital design workflow. And our future work will focus on extending the system to dynamic balancing, multi-plane balancing, and integration with digital twin technology and smart manufacturing system. Thank you so much for your attention. I will be happy to answer your questions.
Dear colleagues, any questions? So this solution, I have a question. This solution, okay, do you hear me?
Yes, sure.
This solution, it's only for CAD system, or it can be applied to other directions?
Thank you so much for your question. Actually, it is scalable. It is the universal approach that can be applied to any procedures that are applicable to. So this is like the information technology that can be used to any direction of to simplify or to automate the mechanical work. But in this study, we used CAD system as the example, as the experimental setup to prove its effectiveness. Thank you so much.
Okay, thank you for your presentation, colleagues. More questions? No? Okay, so the next presenter will be Stadnik. Dmytro Tymощuk and Yuri Klots. Let me share my screen. Okay, let me share my screen. Okay, once more time. Okay. 1 second, please. Dear colleagues, we have conference. Dear colleagues, okay, dear colleagues, do you see the presentation?
Yes, I
Yes,
can see.
Okay.
Greetings everyone, my name is Maria Stadnik and today I'm pleased to present our work entitled ML-based ideas for DNS cache poisoning detection using convolutional neural networks. In this presentation, I will introduce our proposed machine learning approach for detecting DNS cache poisoning attack, discuss the developed CNN-based models, present the experimental results and demonstrate the validation of the proposed solution in a independent IDS prototype. Before introducing our approach, let me briefly explain why DNS cache poisoning remains an important cybersecurity problem. As illustrated in the figure, an attacker sends a forget DNS response for the DNS resolver before the legitimate response arrives. If the forget response is accepted, the malicious IP address is stored in the DNS cache and successfully returned to users. As a result, users may be redirected to malicious websites, their credential can be stolen, and attackers can launch man-in-the-middle attacks without the user noticing. One of the main challenges is that this malicious DNS response often fully comply with the DNS protocol specification. Therefore, traditional signature-based intrusion detection systems have difficulty distinguishing malicious traffic from legitimate DNS package. This limitation motivated us to investigate a machine learning-based approach for DNS cache poisoning detection. Before developing our approach, we analyzed recent studies on DNS attack detection. As shown in the table, research has evolved from traditional machine learning algorithms such as random forest, support vector machines, KNN, towards more advanced deep learning architecture, including CNS and RNN-based models. However, most exciting approach still rely on manual feature engineering or dimensionality reduction techniques such as PCA or statistical feature selection before model training. Our approach differs in three main aspects. First, we introduce a structure session level tensor representation of DNS traffic. Second, we adopt CNN architecture with an efficient channel attention mechanism to automatically extract informative features. And finally, unlike many previous studies, we validate our solution in an independent IDS prototype, demonstrating its practical applicability. The process begins with the DNS package collection. From each DNS, we extract the selected fields from the IPv from the IP, UDP, and DNS headers. Next, these headers are transformed into a structured tensor representation with dimensions 6 by 32 by 8. This representation preserves both the package sequence and the spatial relationships between protocol fields, making it suitable for convolutional neural networks. The generated tensor is then provided as an input to CNN-based classifier, which automatically learns informative features without the need for manual feature engineering. Finally, the model classifies each DNS session as either normal or DNS cache poisoning, allowing the intrusion detection system to generate an alert whenever malicious activity is detected. Now that we have seen the overall workflow, let me explain how the features were extracted. As shown in the table, we extracted header fields from these protocols: IP, version 4, UDP, and DNS. These fields include routing information, transport layer parameters, and DNS-specific information such as a transaction ID, flags, and resource record counters. In total, 32 bytes of header information were extracted from each package. Rather than manually selecting the most important features, we preserved the complete header structure and converted it into bit-level representation. This allows the CNN to automatically identify the most informative parameters associated with DNS cache poisoning attacks without relying on handcrafted features or expert-defined detection rules. After selecting the header fields, the next step was to transform them into the tensor representation used as an input for CNN. One of the key contributions of this work is the proposed representation of DNS traffic. As shown in the figure, each DNS session consists of 6 consecutive packets. From every packet, we extracted 32 bytes of the header information, resulted in 1 by 32 vectors. These 6 vectors are then transformed to form a 6 by 32 matrix, which preserves the temporal order of packets within the DNS session. Finally, each byte is converted into its 8-bit binary representation, producing by 6 by 32 by 8 tensor. This creates an image-like presentation that can be directly processed by convolutional neural network. Unlike traditional approach that relied on handcrafted statistic features, this representation allows the CNN to automatically learn informative spatial patterns directly from the protocol headers. To train and evaluate our models, we used a custom DNS cache poisoning dataset generated using black box fusion techniques. The dataset contains both legitimate and malicious DNS sessions collected into control virtual environment. During the attack scenario, forgetted DNS response were injected to simulate DNS cache poisoning, while the normal scenario consists of standard DNS resolution. To ensure the reproducibility of the experiments, the DNS server cache was cleared before each run, and all captured traffic was labeled at session level. As shown in the table, the dataset consists of approximately 31,000 training sessions and 7,700 testing sessions, with an almost balanced distribution of benign and malicious traffic, providing reliable conditions for model training and evaluation. After training the models, we compared the performance of 4 CNN-based techniques architecture: the baseline of vanilla CNN, CNN with batch normalization and dropout, Model 2 mini residual network, mini ResNet, and CNN with the efficient channel attention mechanism. As shown in the table, each architecture improvement resulted in better classification performance. The addition of batch normalization, residual connection, and finally the ECA mechanism consistently increased the detection accuracy and reduced classification errors. The last model achieves the best overall results with an accuracy, recall, and MCC. The high recall is particularly important for intrusion detection system because it minimizes the number of missed attacks, while the high MCC indicates a well-balanced classification performance. To better understand the classification performance, we also analyze the confusion matrices of the evaluated models. This slide compares the baseline vanilla CNN with the CNN model enhanced by batch normalization and dropout. As we can see, the improved architecture correctly identifies a substantially larger proportion of attack sessions while simultaneously reducing the number of false positive and false negatives. This demonstrates that architecture improvements not only increase the overall evaluation metrics but also make the classifier more reliable in distinguishing malicious DNS traffic from legitimate traffic. And these results motivated us to further improve the architecture by introducing ECA, which ultimately provides the best overall performance. This slide compares two best performing architecture, mini-resident and CNN with ECA mechanism. Both models demonstrate high classification performance, as indicated by strong diagonal wells in the confusion matrices. However, the CNN and ECA model further reduce the number of misclassified samples. In particular, it achieves the highest attack detection rate, correctly identifying 97.62% of malicious session, while also improving the classification of legitimate DNS traffic. These results confirm that incorporating the ECA mechanism enables the network to focus on most informative featured channels, leading to more accurate and robust detection of DNS cache poisoning attack. To further compare the evaluated architecture, we analyze the F-score and MCC, which provide a more comprehensive assessment of classification performance and accuracy alone. As shown in both charts, the performance consistently improves from the baseline model to CNN with ECA. This model achieves the highest F-score and the highest MCC, confirming not only the highest detection capability but also a balanced classification between malicious and legitimate DNS traffic. These results further support our selection of CNN and ECA as a final architecture for deployment. After selecting the best performing model, we integrated it into an intrusion detection system and evaluated it in an independent virtualized environment. As shown in the figure, the experimental testbed was deployed on the QEMU and QEMU hypervisor, where each network component, including the client, DNS server, attacker, and IDS, was implemented as separate Ubuntu virtual machine. Virtual machine was performed using libvirt, while Linux Bridge provided isolated network communication and traffic monitoring to IDS. This environment enabled us to generate both legitimate and malicious DNS traffic in a controlled, reproducible, and fully isolated network, allowing us to evaluate the proposed detection system under conditions that closely resemble real deployment scenarios. After implementing the IDS prototype, we performed an independent evaluation to verify whether the model could maintain its performance in a new environment. To evaluate the robustness of the proposed approach, we perform an independent validation using newly collected dataset that was not used during model training or initial testing. The validation dataset contained 1,500 DNS sessions, including 682 attack sessions, 818 legitimate sessions. The evaluation was carried out in the dependent environment that I presented on the previous slide, the experiments were repeated 4 times, and the results are reported in the mean value with the corresponding standard deviation. Despite the new environment, the model maintained a high level of performance, achieving the accuracy presented on this slide, recall, and MCC. This result demonstrates that the proposed CNN with ECA is robust, generalize well to new DNS traffic, and is suitable for practical intrusion detection applications. To conclude, we propose a novel CNN-based approach for DNS cache poisoning detection and validate it independent IDS prototype, demonstrated its suitability for real-world deployment. Unlike traditional methods that rely on manual feature engineering, our approach automatically learns informative patterns directly from IP, UDP, and DNS protocol headers. Among the evaluated architecture, the CNN with ECA attention mechanism achieves the best performance, reaching 96.68 accuracy, and numbers for recall and MCC are present here. More importantly, we didn't limit our evaluation to offline experiments. We implemented the proposed model in a mail-based intrusion detection system and successfully validated an independent virtualized environment, demonstrated good robustness and generalization capability. In future work, we plan to evaluate the proposed approach on more diverse DNS datasets, including encrypted DNS traffic, investigate the contribution of individual header fields, and assess its performance in real-world deployment scenarios. Thank you very much for your attention. I will be happy to answer your questions.
Okay, dear colleagues, any questions? So I have one. How well would it be your model generalize to real-world DNS traffic since it was trained on fuzzy-based dataset?
Thank you for your question. This is an important point. The training data was created with this controlled fuzzing. To reduce the limitation, we tested the model in another virtual environment with new DNS traffic. The model showed good result, above 93% accuracy, above 95% recall, and 0.89 MCC. This shows that the model works well on new data. More tests are still needed. We plan to test it on the datasets in a real enterprise network.
I see. Okay, thank you. No questions? Okay, let's move on. So the next presenter will be Volodymyr Avseyevich. Are you ready?
Yes.
Okay.
1 second.
Please.
Do you see my screen?
Yes, we do.
So, dear colleagues, my name is Volodymyr Avseyevich, and I'm representing Khmelnytskyi National University. And today I want to present you a research named Cloud-Based Intelligent Architecture and Geometry Cross Processing for Vehicle Number Plate Recognition. So, as a start, we will discuss some key points about literature that are presented in this aspect of researching. So we have some 3 main approaches to automating license plate recognition. It is deep learning models, edge device recognition, and general purpose APIs. When we use deep learning LPR models like YOLO, CNNs, we need expensive discrete GPUs, and it is not economically practical in some cases. But when we try to outsource this to edge devices with standard CPUs like Raspberry Pi or some kind of microchips, microcontrollers, we will lack computational power, and this create thermal and latency bottlenecks, making our solving this method of solving inefficient. And by the other hand, we have general purpose APIs like Google Cloud Vision. They solve these hardware limits by generally outperforming some other methods, but they introduce special fragmentation and disjointed test blocks as well as optical illusions. So the objection of our study was to develop a resource-efficient cyber-physical system using cloud OCR with a local geometric and linguistic post-processing layer. So again, more clearly, we have three approaches. First is YOLO or CNN. The second is Tesseract. It is a popular OCR engine that can work locally, but it needs fine-tuning on edge device. And the third option is Cloud Vision APIs that we choose to solve this problem, but they need some methods to eliminate this lack of geometry constraints, fragmentation, and disjointed text blocks. So we develop models that consist of two global steps, and first step is geometric model. It has two steps. First is bounded box expansion. When Google Cloud Vision recognizes objects from the picture, it returns a bounding box array, which is consist of cars, labels, other models, logos, and etc. The first thing that we do is we compensate this localization error by shifting outwards bounding boxes by exact coefficient. These coefficients are alpha and beta. We use 5%. This is a heuristically ideal condition for this step. And by using these formulas, we will shift all vertices in the outer array. By doing that, we compensate these errors. And the next step is point-and-polygon matching. When we have these extended bounding boxes, we can check if the text that is interesting us, like vehicle polygon register plate, if it is falling inside the vehicle polygon. We can check this by recursion algorithm by checking the number of intersections with edges and horizontal array from the point. When we know the text falls in the vehicle polygon, we can assign this polygon with this license plate. And the next step is formal grammar. We can rewrite this license plate string with some form of regular expression, which consists of numbers of characters before and after the plate number, which is represented as sigma. We define set of Ukrainian letters and letters that looks like digits that look like letters. This is 0, 1, and 8. OCR engines often recognize some letters as digits and vice versa. We have two Ukrainian letters at the start of the number. Then we have 4 digits and letters that look like digits is O, I, B, and J. We have 4 of these characters, then again 2 Ukrainian letters, and again any number of characters after the plate number. Next, we have 2 tables of transforming that tau English to Ukrainian, which converts similar Ukrainian letters and English letters. It is just for some. It will be more easy to use number with Ukrainian letters than with English letters, even they are the same. Next, we have phi letters to digits and digits to letters, which converts similar looking letters to digits and vice versa. And when we have fully recognized number string with 8 characters, we will use this transformation for first 2 characters, then from third to 6, and then from 7th to final step is translating these letters, and we will have final license plate that we are confident that it is correct and using the exact format and transform digits to letters and vice versa. Also, we have some fallback mechanisms when the system doesn't see any car bounding boxes or license plate objects. Firstly, it will see if there are car bounding boxes. If there are not, we will scan all the text on the image and see if there are some license plate. This is done because we expect setup with camera in front of cars that's driving in the parking space, and essentially they always have this license plate. So if we have license plates, that we will try to recognize it. Here is our CPS architecture. It consists of 3 main blocks. First is OpenCV image getting APIs. It is written in Python. This acts as like a edge buffer for HSP connection that drops corrupted frames and ensures that we don't reuse duplicated frames when there is no new info. For example, there's a long time with no new cars as a parking space. We will not send these images to get recognized by Google Cloud Vision. We will just wait. Next is core REST APIs that's written in Laravel framework. It makes these Google Cloud Vision requests. It executes all geometric and formal grammar models and returns this result as JSON. And the third layer is the client layer. It is consisting of React Native mobile app and web dashboard. We evaluated our system on custom dataset of 215 photos with 245 vehicle plates. We labeled it via custom annotation tool. This tool was designed because datasets that are presented on the internet don't either have labels with plate numbers that is entered in some metadata of JSON or anything, or it is just numbers of plates, but we want to test system on the picture of real cars. So we designed this tool to filter, to assign these categories to evaluate system. And we have a result presented in this table. We have baseline implementation that is only using Google Cloud Vision, no transforming, no optical recognition, no trying to fix optical recognition errors, and etc. And we have our hybrid implementation with formal grammar and geometric implementation. So what can we say about these results? We have some precision recall trade-off. We decrease our precision by less than 2%, but we greatly increase our recall to 90%. And therefore we gained some percent of F1 score and accuracy score. We analyzed why we dropped precision, and we studied these causes of false negatives and positives. So false negatives that affect the recall are dropping vehicles with personalized custom plates. As we show in this picture, we have plate that is consists only for GNAP. It is not some standard plate format, but it is valid. And when we can't recognize some text with the OCR engine, it will also drop it and get false negative. The false positive, which affect the precision, it is recognizing E as F or BSU. For example, as on the first picture, there is number with EO at the end, but the system recognizes it as FO, and it is false positive. Also, we have some cases when other objects like leaves or reflections, shadows, it is overlapping the license plate, and it also can't recognize it correctly, like misinterpreting I as P. Also, like shown in the CIS picture, we have very pixel degraded photo, and we can be sure that this number is 3 or 1. The system thinks it is 1, but it's actually 3. We have also developed 2 user interfaces. The web dashboard that is rendered by the server. It is designed for security personnel on the parking space, and this shows categorized digital metadata like logos, text on car, and license plates. Also, the same functionality is presented in mobile app dashboard. It is a React Native client with asynchronous state updates, and it is designed for end-user access. Currently, it is presented as manual entering photo app, but because we have not set up with some cars driving in with camera in front of them, we designed it for future use this Python image getting API, but currently it is in this form. So in conclusion, we can efficiently run real-time license plate recognition on edge CPUs by offloading it to the cloud. We can use recasting geometry and linguistic grammars to reconstruct fragmented text, even when using general purpose models. And we achieved a balanced advanced score of 92.9% with a precision of 95.9, making it viable for strict access in smart parking. That's all. Thank you for your attention. I want to answer a question if you have any.
Thank you, Volodymyr. Okay, dear colleagues, does anybody has questions? Okay, I have one. What part of the recognition pipeline has the greatest impact on your overall accuracy?
I think.
Mhm.
Thank you for the question. I think that it is essentially just OCR engine, because if you don't have data to work with, we can't fix it. We can't recognize errors if there are no recognitions. So that's why we analyzed approaches to do it. So we know that Tesseract engine is not suitable for this type of recognition. We know that YOLO or CNN are just too heavy on resource consuming, and therefore we are leaving it to the Google engine that is constantly improving, and it essentially has the greatest impact on this task.
Okay. Colleagues, more questions? No? Okay. In this case, I suppose that we have coffee break till 20 o'clock. So have a rest. We will continue. See you. So, dear colleagues, let's continue our workshop. Okay. And the moderator will be my colleague, Andrei. Are you ready?
Yes, hello. Okay, we start. Yeah.
Sure.
Okay. First of all, we are delighted to welcome you to the International Workshop of Intelligent Information Technologies and System of Information Security. And let's us begin with a few notes about today's schedule. We have 10 presentations. Each presentation is allocated 10 minutes, followed by 5 minutes for question and discussion. We kindly ask all presenters to adhere to the time limit and avoid exceeding the allocated presentation time so that we can keep the workshop on schedule. Also, we will proceed according to the conference program in the established order. However, there are still 3 presentations remain from the first session, so we will hear those first. Are there any objections? No. Yeah. Okay. Are the speakers from the first session present here?
Yes.
Yes. Okay. Vyacheslav, one moment. I check your paper. It's Yaroslav Hladký, Miroslava Hladká. Yeah.
Oh, it's maybe Vyacheslav Kovtun now.
Yes, I'm Vyacheslav Kovtun, and my presentation was last at the previous
Okay.
session.
Okay.
Please start.
Yeah. Okay.
I can start.
Yes.
Thank you. Give me a minute. Can you see my slide?
Yes, we see.
Yes, we do.
Thank you. Okay, so dear colleagues, let me introduce my work. Today I will present our work on risk-sensitive decision-making for alert escalation in security operation centers under resource constraints. The central problem is that modern SOCs receive a large and high variable stream of security alerts, while analyst capacity and deep investigation resource remains limited. Therefore, for every alert can be investigated immediately, the system must decide which alerts should be escalated, which should be defeated, and how to avoid overload. The motivation comes from the operational reality of modern security operation centers. The typical SOC may process thousands of alerts per day. Many of them are false positives, but hidden among them are real attacks that must not be missed. The difficulty is that analysts work under strict resource constraints, which when alert volume increases, backlogs, accurate response delay grow, and the probability of missing critical incomes becomes higher. This means that alert escalates is not simply a classical classification problem. It is a sequential decision-making problem under uncertainty, where each decision affects both current detection quality and future workload. Exciting approaches solves different parts of the alert escalation problem. Rule-based systems are simple and iterable, but they cannot adapt well to challenging attack behavior. Supervised machine learning employs classical accuracy, but it is usually ignores QAQ dynamics and future workload. Reinforcement learning can model sequential decisions, but standard risk neuronal RL often optimizes average reward and does not control extreme overload events. Human in the loop and learning to differ approaches reduce analytics workload, but they rarely include explicit QAQ and resource constraints. The main research gap in that exciting methods usually do not integrate the hidden attack states, QAQ dynamics, resource limitation, and tail risks control in the single optimization framework. The object of this research is the alert escalation problem in the security operations control centers under limited analytical resource. The aim of the study is to develop and validate a model that minimizes high percentages QAQ length, control the risk of missing attacks, and respects the available budget for deep analytics. Let's move to the theory part of this presentation. The first theoretical component is the POMDP formulation. In a real SOC, true security state is not directly observable. The system does not show which centrally whether an alert corresponds to design activity instead it is received noisy operation from the same ideas, IDR and other and related monitoring systems. To handle this uncertainty, the model maintains a belief state. This belief is a probability distribution over possible hidden attack states. After each new observation, the belief is updating using Bayesian filtering. Thus, escalation decisions are not based on the single QAQ state, but on the full probability distribution over possible states. The second component models QAQ dynamics and operational cost. Incoming alerts from the backlog. At each time step, the selected action determines how many alerts can be processed and how many remains in the QAQ. The QAQ therefore depends on two competing processes, the arrivals rate of new alerts and the service capacity of the SOC. The cost function combines several operational factors, missed attack risk, delay cost, analyzed workload, resource usage, and switching cost between actions. This is important because a locally good decision may create future overload. The POMP is transformed into a constrained Markov decision process by using the belief state as a part of the observation state. The policy must optimize long-term performance while satisfying operational constraints. Those constraints include missing attack risk, backlog risk, analyst workload, and deep analysis resource usage. We use Lagrangian formulation to include those constraints in the optimization problem. The policy is trained using proximal policy optimization or PPO. The key distinction from standard reinforcement learning risk sensitivity instead of optimization only average performance, the model explicitly targets tail risks, the rare but dangerous overload simulations that are critically for SOC stability. Here we can see experiment design and the experimental validation was conducted on two benchmark cybersecurity datasets. Dataset A is the SIG IDS 2017 and dataset B is UNSW and B15. Both datasets were transformed into SOC-like alert streams. Network flows were aggregated into 1 second intervals, which allowed us to reconstruct the alert level intensivity over time. The data were split chronologically, and this design ensures that performance differences are caused by the decision model itself, not by different experimental conditions. Here we can see the first result. Figure 1 shows the empirical alerts arrival instantivity and rolling variance for both dataset. The most important observation is that alert arrivals are not stationary. They are bursty and highly variable. Outcoming such periods, the queue may grow rapidly, become alert-arrived intensivity approach available processing capacity. This result justifies the need for queue aware and risk-sensitive model. Average-based control is not sufficient when operational risk is constrained in the bursty periods. Figure 2 shows how stationary backlogs depends on arrival intensivity and available processing capacity. The surface is relatively smooth under the moderate load. However, when the system appears the stability boundary, backlogging increases sharply. This performs the nonlinear nature of SOC overload and explains why tail risk control is essential for the stable escalation management. Figure 3 presents the Pareto frontier between the total operational cost and missed attack risk. The figure illustrates the fundamental trade-off of SOC escalation. Reducing the probability of missing attack usually requires more deep analysis when increases operational cost and resource usage. Figure 4 demonstrates how belief evolves during policy escalation. The dominant posterior probability increases over time, meaning that the model becomes more confident and the hidden attack regime. At the same time, belief entropy the entropy decreases when which indicates the reduction of uncertainty. The model does not only react to alerts, it generally accumulates information and uses this information to make more stable and better grounded decisions. This figure 5 compares the Ninitri 9% of QAQ length or P99 backlog for the proposed model and 3 baselines. The comparison is performed for different values of the risk average parameters. Across both datasets, the proposed model achieves the lower P99 backlog over the analyzed parameter range. Figure 6 evaluates policy stability through policy variance under different values of the registration parameter tau. Those constraints include missing attack risk, backlog risk, analytical workload, and deep analytical resource usage. We use Lagrangian formulation to include those constraints in the optimization problem. The key destination for standard reinforcement learning is risk sensitivity. Instead of optimizing only average performance, the model explicitly targets tail risks, the rare but dangerous overload simulations that are critical for SOC stability. I'm sorry. Yes, we see we see the table 1. Table 1 presents the ablation and sensitivity analysis. The full proposed model achieves the best overall performance on the both datasets. When risk sensitivity is removed, P99 backlog increases to 129 and dataset R for dataset R and 121 for dataset B. When belief information is removed, false escalation rarely increases substantially, up to 10% for dataset A and up to 11% for dataset B. This shows that each component of the framework contributes the performance and the model removes robust and parameter perturbation of approximately 20%. This is the conclusions. To conclude, this study proposes an integrated model for risk sensitivity SOC alert escalation under uncertainty and resource constraints. The main contribution is the combination of partial observability, Bayesian belief updating, nonlinear vacuum dynamics, constraint optimization, and risk-sensitive reinforcement learning in one framework. The experimental results demonstrate three main findings. First, SOC alert streams are bursty and often approach quasi-critical load constraints. The second is the QAQ backlog grows non-linearly near the stability boundaries, which makes tail risks control necessary. Third, the proposed model reduces the extreme backlog stability policy behavior and control false escalation while respecting resource limitation. Overall, the results show that SOC escalation should be treated as a risk-sensitive control problem when rather than a simple classification task. So, thank you for your attention, and I'm ready to answer your questions.
Thank you, Vyacheslav. Colleagues, maybe you have some question? Okay, maybe I have one question. Vyacheslav, please say, do you test your approach in real world system? Not synthetic data set?
Not yet, because I haven't such an opportunity in, especially in this time of war, and all those centers are not available for science. But I hope that I will have some opportunity in this case, contacting with European colleagues from Poland and Germany. So I hope that I will update these results after some time and present you once more.
Okay, thank you. Okay, maybe someone have another question? No? Okay, Vyacheslav, thank you. Your report is finished.
Thank you.
We move up. Okay. So the next report will be hardware configuration space of intelligent information technology for rehabilitation support. Does the author present of such a report? Okay, move next. Modified VLESS with dynamic channel allocation to prevent behavioral analysis. Okay, also absent. And the last one in the first section, it's topology and evidence-aware risk assessment for microservice-based systems. As the author presented? No, yeah, okay. So move to the second section. And in the second section, the next report will be intelligent system for automatic detection of web application vulnerabilities and threat classification. The author is Andrei Nichipuruk, Andrei Selsky, Andrei Ramsky, Dmytro Mikuliak, Thomas Socher. I will present this report. One, please. Have you seen my screen?
Yes.
Yeah, okay. Okay, thank you. My topic today is an intelligent system for automatically detection of web application vulnerabilities and classification threat. The core idea of proposed method, it's a hybrid architecture that combines graph neural networks and large language models together with a unified way of normalized CAST, DAST, and CSA results and dynamic risk score that reflects real business context, not just technical severity. Let us start with the problem. Modern pipelines are not short on tools. They are fragmented. CAST, DAST, and CSCA each output reports in their own format, with no shared taxonomy. Static analyzers generate huge numbers of false positives, which cause alert fatigue, so real threats get ignored. And the standard CVSS score only measures technical severity. It says nothing about whether the affected system in the test sandbox or a public payment gateway. As a result, our 18% of web application ship with at least one critical vulnerabilities. Looking at prior research, there are two strong but one-sided directions. Graph neural networks approaches like BGNN for VD and Line VD are excellent at tracing data and control flow code and localizing flows precisely, but they miss semantic context like comments or business intent. LLM-based approaches like IRIS are excellent at understanding that context and catching logic flows, but they struggle with vulnerabilities that span multiple files. No existing system combines normalization, so this GNN plus LLM synergy, and contextual risk scoring into one closed cycle. Our system, we call it is ESAVDWA, starts from a format model. Each web application is treated as a set of artifacts, source files, dependency graphs, configs, HTTP requests. An embedding operator phi maps every artifact into a high-dimensional feature vector. Then, to solve the isolation problem between scan types, we defined a unified incident space that merge SAST, DAST, and SCA results, and a normalization operator N that maps all of them into the same feature space. So a statistic suspicion and dynamic configuration of the same issue collapsed into one inherited record. In practice, this means three input streams. SAST looks at static source code for structural issues. DAST probes the running application with real HTTP request, simulating an attacker. SCA scans third-party dependencies for GNOME CVS. All these fit into the normalization model, which is really the glue of the whole system. It takes those heterogeneous JSON, XML, and CRIF reports and turns them into one consistent, deduplicated, cross-correlated representation. At the core of the system is the hybrid model itself. The GNN branch represents code as a directed graph of operators and variables connected by the date and control flow edges, and traces how unsafe values propagate toward a dangerous sink. The LLM branch uses transformers self-attention over the code tokens and comments to capture semantic intent. For example, recognizing that a function touch payment data. Their output are combined through a simple weighted fusion formula. P final equals alpha times P GNN plus 1 minus alpha times P LLM, where alpha is tuned on the validation set. This is exactly the complementary we saw was missing in previous work. Putting all together, the system runs in a 6-stage pipeline. Stage 1 ingests the raw data source. Stage 2 normalizes and deduplicates them. Stage 3 is a hybrid GNN plus LLM ensemble running in parallel. Stage 4 aggregates their two probability outputs from the weighted fusion. Stage 5 turns that into a prioritized risk-scored output rather than just a flat list of errors. And stage 6 feeds a confirmed incident back into training, closing the loop and steadily reduce the false positive rate over time. Stage 5 deserves a closer look, because this is how we fix the CVSS blind spot. The total risk is the base CVS score multiplied by 2 coefficient. Key, which reflects business criticality of the affected model, low for the test environment, high for the production system handling personal data, and K exposure, which reflects the real network reachability from the DAST results, approaching 1 for a public endpoint and dropping sharply behind authentication or WAF. So a severe bug in an isolated sandbox is correctly pushed below a moderate bug on a public payment API. To evaluate this proposed system, we built a data set of just over 14,000 security events. About 62% are real-world vulnerabilities drawn from 20 open source Python, Java, and Node.js projects, matched to CVS through Git history, which fusion and line-level labels. The remaining 38% are synthetic, generated through code mutation and HTTP fusing to cover race CWE classes that were underrepresented in real data. We split everything in portion 17, 15, 15 into train, validation, and test sets. Here we have the result of the held out test set. Random forest represented a classic SAST style baseline, reached an F1 of 0.77. The standalone GNNM improved that to 0.84, thanks to date flow tracking. The standalone LLM reached 0.86 by understanding context. But the hybrid together match these two machine learning approaches, we reach F1 measure of 0.19 and a ROC AUC of 0.95. So report is finishing. Maybe someone have question. Thank you. Okay. No one have question. Okay. Thank you. So let's move. And the next report will be multi-factor vectorized search for relevant scientific articles and adaptive deep learning pipeline method. Are the author present?
Yes, good day, I'm present.
Okay, you're welcome.
Thank you. Good day, dear colleagues. Today I will present our research titled Multi-Factor Vectorized Search for Relevant Scientific Articles and Adaptive Deep Learning Pipeline Method. The amount of scientific literature is growing very quickly, and manual filtering of publications becomes increasingly difficult. In many domains, especially interdisciplinarity ones, the same idea can be expressed with different terminology. Traditional keyword-based search is useful, but it often cannot capture latent semantic similarity between a query and a publication. At the same time, pure semantic similarity is also not a way scientific, because it may ignore publication quality, recently, and citation context. Therefore, the research problem is to retrieve articles that are not only semantically relevant, but also structurally valuable for academic and educational use. The main contributions of the study are the combination of vector search based on embeddings with meta-ranking of results by structural features. This combination allows to ensure not only the content correspondence to the search query, but also to take into account the qualitative and temporal characteristics of applications, which is especially relevant in the educational process for the analysis of modern scientific information. This slide shows a general pipeline of the method. The input is a search query, which can include a title, abstract, keywords, authors, and another available fields if it needed. At the first step, the query is converted into a vector representation using the All-Mini LM-L6 version 2 model. At the second step, phase performs vector search and returns a set of potential relevance articles. At the third step, the candidate articles are re-ranked using the multi-factor relevance function. As a result, the system returns top N articles and that are relevant to the user query. Each document in the collection is described by a set of text fields and metadata. We use the title, abstract, keywords after. The user query is represented in a similar aggregated way.
they include the title component, abstract component, keyword component, and after component. This is important because academic search often depends on more than one textual field. After aggregation, the query is passed to the encoder function f, which produced a latent vector representation. All documents are vectorized in the same semantic space, so we can compare the query and articles by vector similarity. For the text vectorization, we use one moment. For text vectorization, we use the all-mini LM-L6 version 2 model. It belongs to the sentence BERT family and is optimized for production sentence embeddings. The input text is first tokenized using the word piece tokenizer, then token positional and segment embeddings are processed by transformer encoder blocks. The model has 6 transformer layers and 8 attention heads. At the output, mean pooling is used to produce one compact vector for the whole sentence of query. The final embedding has 384 dimensions, which is efficient for large scale retrieval. The final relevance score consists of 4 components. The first and most important component is semantic similarity between the query and the document. The other 3 components are normalized publication year, normalized citation count, and venue prestige. In our experiment, the semantic components has weight 0.7, while year, citation, and venue prestige each have a weight 0.1. This means the semantic relevance remains dominant, but metadata helps improve the ordering of results. For experimental evaluation, we use the research paper dataset from Kaggle. It consists about 1 million scientific articles for different research domains. The dataset includes important fields such as title, abstract, authors, venue, year, number of citation, and references. These fields allows us to test both semantic search and metadata-aware ranking. This screenshot shows the development Sparse search web application. The user can enter a query and select the search criterion, for example, title, abstract, title, and abstract of authors. The system returns a ranked list of application. For each result, the interface displays the title, authors, publication venue, citation, count, and year. This makes the output interpretable for user. This slide shows architecture of a website. The architecture consists of a client service and a relevant article search service and a database. The relevant articles search services receives the request, converts it into a vector representation, uses face to search for candidate articles, and ranks the result using the relevance function. The experimental protocol includes 100 random aggregated search queries. These queries were generated using titles, abstracts, and keywords from publication across different scientific domains. 3 IT experts manually assessed relevance using a binary scale. If there was a disagreement, the final relevance label was assigned by majority weighting. We compared the proposed method with TEF-EDF, BM25, universal sentence encoder, and mini LM-L6 without metadata, and our approach with metadata. The evaluation metrics were semantic precision, NDCG, and MRR. The table shows that the proposed method achieved the best values for 3 metrics. Compared with mini LM-L6 version 2 without metadata, we propose method improves all metrics. This confirms that metadata-aware ranking provides an additional benefit after semantic retrieval. The difference is especially important for academic search because the user usually checks only the first results. Therefore, placing relevant document higher in the ranking has a practical value. The improvement comes from combining two types of information. The transformer encoding captured semantic similarity between the query and semantic articles, while metadata reflect additional quality signals. The NDCG chart shows that the proposed method places relevant documents close to the top of the list. This is important because user often really off the first page of a search result. In other words, the method does not simply find relevant articles in the list, it improves the position is the ranking output. The first limitation is the dependence of metadata quality. If publication year, citation count of new information is incomplete or inaccurate, the ranking quality can decrease. The second limitation is computation cost at the indexes stage. A large corpus must be pre-vectorized, and this requires additional resources. Future work will focus on integration citation context, adding personalized user profiles and supporting dynamic research trajectories. These extensions can make academic search more adaptive to the needs of individual researchers. And to conclude, we propose an adaptive deep learning pipeline for multi-factor vectorized search of scientific articles. The method combines mini-LM L6 version 2 embeddings, phase indexing, and metadata-aware rankings. Experimental results show that this combination outperforms lexical baselines and semantic search without metadata. And obtain high values of matrix, and this confirms the effectiveness of the proposed approach for academic search task. The method is scalable and can be integrated into educational informational system and academical digital libraries. Thank you for your attention.
Okay, thank you. Colleagues, maybe you have question. Okay, maybe I have one question. Alana, please say how did you choose the coefficients alpha, beta, gamma, and delta? I think in back. It's I think it's your result in
Yes.
yeah.
Yes. We choose these weights by experimental ways. We choose it empirical.
Okay, thank you. Okay.
Thank you.
No one question. Okay, thank you. The report
Thank
is
you.
finished. So the next report will be the method of parallelization of dynamic sequential system programs using network of multi-phased processed. Автors Олег Савенко, Микола Федула, Ян Рапчан, Кирило Возний, Жири Балей, Анатолій Барабаш. Who will be present?
Me, Kirill Возний. Hello.
Okay, you're welcome.
Let me share my screen. Okay, you should see the presentation right now, right?
Yeah, we see.
Yeah, okay, thank you. So hello everyone, and thank you for being here. So my name is Kirill Возний, and on behalf of co-authors from about this paper, I will present a method for parallelizing dynamic sequential system programs using network of multifaceted processes. In the next few minutes, we will talk through the problem, core idea, the method, and the experimental result. So basically, the problem. Today's computers basically built on multi-core processors and distributed platforms, which offer real potential for parallel execution. But yet much of our system software was written to run sequentially on a single thread, each instruction is waiting for the previous one to finish. And as a result, most of the cores sit idle and hardware is underused. The goal of this paper is to try to use the cores fully without basically radically rewriting the program structure, rewriting it from scratch, and so on. Why the automatic parallelization can be hard? Because unlike static algorithms, dynamic system programs build their execution flows while they run. They carry complex data dependencies, irregular structure full of conditional branches, tasks that are created at runtime, and shared resources that must be synchronized. Any one of these complicates parallelizations. Together, they basically defeat the traditional automatic methods, and that is exactly why a specialized approach is needed. Our contribution is to treat the program as a network of processes. Now, like, we do not remember Bernstein conditions, dependency graphs, or Amdahl's law. Those are like well established already. The contribution is integrating them into a single coherent transformation pipeline built specifically for dynamic systems programs. And it's at the center of that is basically what we call the multifaceted process, one universal computational element that computes, communicates, and synchronizes all at the same time. The combination is what makes basically this model is flexible. The model is, you can see it in the screen. It represents a network of these processes. Each hexagon is a multifaceted process working on the part of the computation, and the arrows are, you can say, data channels that carry intermediate results between processes. And the central node coordinates the work. Because the processes run in the same time and exchange results through these channels, the total execution time comes down. We have the three program patterns we target, where hidden parallelisms tend to be. First, independent function call. Those results do not depend on one another. Second, independent instructions pass inside a single procedure. For example, applying a noise filter, a contrast enhancement, and a brightness histogram to an image all at once. And the third one is the independent loop iterations, such as computing a sum of the squares over the array and then combining the result with a reduction. Each pattern comes with formal conditions that tell us when the parallel execution is safe. The rules basically when the parallel execution both safe and worthwhile. For that, we have the three rules. First, independence, which is Bernstein conditions, that two operations can run together only if neither one overrides what the other rates overrides. Second, the fit the hardware. This is added first condition. The number of parallel tasks should match the number of available cores. And the speed we gain must exceed the overhead of the coordinating them. And basically the third one is the Amdahl law. The sequential part of the program sets in the hard ceiling of the achievable speed up, no matter how many cores we can add. So the method itself is a pipeline of 8 stages. We classify the program, analyze the structure, and build the dependency graph. Then we decompose it into functional blocks, turn these blocks into the multifaceted processes, and wire them into a network. Finally, we identify the regions that can run in parallel and map them into actual cores. The important point is that this transforms how the program executes. It never changes what the program computes. The experiment to evaluate, we built a test streaming log pipeline, 7 processes, like from producer that generates messages through parsing, filtering, analysis, statistic, aggregation to the logger. So each run as a thread and are connected by thread-safe channels. We run 3 input sizes, 100, 200, and 300, 500 messages on 4 threads or cores. And we verified that filtering and aggregation produce the correct results throughout. The results was the parallel execution is about 2 to 2.5 times faster than exponential. For 500 messages, for instance, the percentage time drops from 28 seconds to under 11. And just as importantly, the speedup stays stable across all the 3 input sizes, which tells us that process network structure holds up as the workload grows. And the efficiency, it ages down only slightly as the load grows. We understand exactly why. So the channel queues begin to fill, synchronization with mutex and conditional variables add some contention. And copying messages payloads costs CPU time. So these percentages tell us that we're making good use of the software with only moderate and well understood coordination overhead. Why it does matter? Because like in the future work, we can also use it for defense systems, often which have often to like many alternative configurations at the same time. And synthesizing honeypots and decoy network structure, for example, mean weighting different attackers' paths, defensible responses, and resources trade-offs. These are partially independent tasks, which can actually make a good fit for our multifaceted process networks. And a detailed cyber security case study is basically what we are planning. The practical path. So we formalize the dynamic system program as an analyzable network of interacting processes, and without any writing the code, adding the hardware for condition to the classic criteria. Looking ahead, we plan to extend the method to distributed computing environments and probably to the cybersecurity case study, as I mentioned before, on honeypots and decoy network synthesis. So, yeah, thank you for your attention. And do you have any questions?
Okay, thank you, colleagues. Maybe you have some question. Okay, maybe I have one. Kirilo, please say what is main advantages of your proposed solution in comparison of GNOME solution?
First of all, like we minimize the code rewrite because we have the formal framework which transforms traditional sequential systems to the parallel structure. And I would say maybe we maximize the multi-core hardware utilization. So we can effectively handle the dynamic runtime workload, and we can guarantee the data correctness and race-free execution because we established that the base laws should be there, like Bernstein law. And it can be a way for basically why we actually take a look at it, because the architecture ability to run it partially can simultaneously make this highly advantageous for high-through security tasks. Yeah, does it answer the question?
Okay, thank you. Maybe someone question want to ask? No. Okay, thank you, Kirilo.
Thank you very much.
Next, the next report will be an intelligent method for the analysis of fiscal incentives for green investment. Who will be present?
I will be present, Oksana.
Okay, you're welcome.
Thank you. Can you see my presentation?
Yeah, we see you.
Okay, thank you. Greetings from the West Virginia National University. The topic of our research is an intelligent method for the analysis of fiscal incentives for green investment. In the context of martial law in Ukraine, post-war recovery, the development of effective financial mechanism for ecological modernization and green investment support is becoming increasingly important. The study focuses on creating an intelligent method for evaluation fiscal incentives as a tool to improve the use of financial resources, promote the green transformation of the economy, and support Ukraine's European integration priorities. The effectiveness of tax, budgetary, customs, and grant support instruments for green investment is increasingly becoming the subject of modern scientific research, as those mechanisms directly influence the sources of Ukraine's green transformation and ecological modernization. A figure of one shows distribution of scientific papers from the Scopus scientific database, but the key phrases fiscal incentives and green investment according to the author's affiliation. As the development of effective fiscal mechanism to stimulate green investment requires as intelligent assessment of the relationship between budget programs, tax and custom instruments, investment activity, and environmental modernization. Environmental taxes, budget, expenditure tax, and custom grants and other support tools are important elements of the green transformation, but the effective depends their ability to generate real capital investment. The proposed approach is based on an integrated system of indicators that combines macro-financial, investment, and incentive-related parameters. Those indicators can be used for fuzzy set analysis to evaluate the effectiveness of fiscal stimulation of green investment. The key indicators we can see on this picture is it's environmental tax revenues, budget expenditures on environmental protection, capital investments of environmental protection, current environmental expenditures and enterprises, and fiscal incentives for green investment, including tax, customs, and grant instruments. On this slide, this figure shows a general view of a fuzzy system. The taxes paid indicator that was a first indicator in this model reflects the amount the environmental taxes paid by business entities and shows the financial contribution to compensating the environmental damage and supporting environmental protection measures. In the fuzzy model, this variable and next four variables diminish linguistic terms small, medium, and high, which makes it possible to assess how environmental influence enterprise motivation and capacity to increase green investment. On this picture, we can see view of the taxes paid variable. The budget enterprise expenditures variable characterize the dynamic of budget expenditures of environmental protection. Figure 4 shows a general view of the budget variable. The next one, within the framework of the fuzzy model, the capital investment variable reflects the volume of the capital investment by enterprises aiming at environmental protection. This indicator characterizes the business entities to invest in production modernizations, the introductions of environmental technologies, emission reduction, and the natural resources. This picture shows a general view of the capital investment variable. The next one, within the framework of the fuzzy model, the enterprise expenses variable characterize the current expenses of enterprises on environmental protection. The indicator reflects the regular financial and expenses of business entities for the maintenance and environmental protection equipment. This picture shows a general view of the enterprise expenses variable. The last one, the financial incentives for green investment variable, characterize the level of use of financial incentives and the active green investment. This picture shows a general view of the fiscal incentive variable. And the result of this model for assessing the effectiveness of fiscal incentive for green investment in Ukraine is a generalized assessment of the fiscal incentives for green investment in Ukraine. This output represents by three terms, such as low, moderate, and high, which characterize effective and systematic stage support for green investment. This approach makes it possible not only to determine the overall level of effectiveness of fiscal policy, but also to identify the key factors that have the greatest impact on the development of green investment. This picture 8 shows a general view of the result of our proposed model. The constructed model works correctly, which is confirmed by result shown in picture 9. This slide presents practical value and conclusion of the study. The proposed fuzzy model can be used to assess the effectiveness of fiscal incentives for green investment, support decision-making in green fiscal policy, and improve the allocation of financial resources for environmental modernization. It can also be applied by public authorities and auditors to evaluate tax, budgetary, customs, and grant support instruments and their impact in Ukraine green transition. Thank you for your attention.
Thank you. Colleagues, have you a question? Okay, maybe I have one. Oksana, please say, how many rules in your fuzzy inference system?
1023.
Oh, it's too big.
Yes.
Okay. Okay. Questions? No questions. Okay, so thank you. Your report is
Thank
finished.
you. Thank you.
And we move next. And the next report will be an adaptive stabilization framework for resilience information system under dynamic and adversarial conditions. Who will be present? Okay, next, so go on, next report. Modern information space, manipulations, existing analysis methods, and model of integral analysis. Who will be this present?
Yes, I'm here.
Okay, you're welcome.
Let me present it. Okay. One moment. Yeah. So I hope you're, sorry for that moment. So I hope you see the entire presentation. So I'm the representative of Chernihiv National University, working on NLP topic, applying on the informational sources. So basically the role of information in the world actually is one of the biggest tools to manipulate the society, and it's especially highlighted during the Russian-Ukrainian war, when a lot of news and information come from the internet, and the problem actually is that mostly of them are unverified and unknown authorship channels. And the problem is that the responsibility for filtering the fake news and identify the hostile sources is put on the end user shoulders, which is the average person in the society. So as we saw, there's a lot of sources that grows in numbers, which consequently make the volume of the text bigger, and it's kind of unhandled by a human brain. It does not have time to do that. So it makes us be able to transform an intuitive task to an engineering one. Actually, we are focusing on sources that are related to like news, military, political topics, etc. So basically, let's talk about few manipulations. There are a few of them, and for example, Russia took the information as a weapon, and it is managed by their government. And two main techniques that is used in social media is the cascade narratives and amplification pyramid. So the first one is about spreading the same passage about any topic, but for different audience, with rewriting them to different groups, like people with the nostalgia about USSR or like Russian wall, etc. So another technique is about spreading that uh, uh, the fake news hierarchy from the government up to the down to the official sources, unofficial sources, some bloggers, and at the end is bloggers. So at the end, in few hours, that news sounds natural and true. So I tried to analyze two of existing approaches that handle that topic, specifically identifying the sources. And what I take into account that some of them have no multi-factor approach. For example, I detected like three groups of these approaches, like graph-based, based on implicit connections between sources. Next one is the text-centric, which is kind of excluding the name of source, but more about detecting the emotionality topics and the regard of the authorship, without regard to authorship, yeah. And for recent years, there are some hybrid systems that took into account few factors in order to compare sources. So here the table of analyzed sources and looking at which factors do they analyze, so like semantics, time, and network between them. And if when most of them are like partially or does not analyze that factor at all, just one of them, like MIDAG 2024, it is the most advanced approach, which took into account all the vectors, but actually it's limited to the COVID topics, analyzing the news about COVID. And it's another limitation, it is keyword based, looking only for sources by keywords. And what should I emphasize that none of these technique, of course, is not applied to Ukrainian information space and Ukrainian text as well. So the object is processing of analyzing the information space, and actually we are considered of mathematical model that calculate multi-factor score. So as my proposal is to create a integral model that counted few factors where each factor have its own weight. So be more clear. So let's say we have factor one, constant similarity of text field, which means that based on vector similarity, we count how good two channels are similar between them, and we have one score. So here's an example of that. You have a heat map for between 23 channels crossing, and here we just looking at which channels had the most similarity. And as we say here, there are some of them which mostly have like pro-Russian audience. Ukraine, 2020 rule, resident UA, etc. Next factor is my Outred approach, which took in account both similarity, text similarity, semantic similarity, and time. Actually, how it works is like taking a message from channel A, comparing with the most similar messages from the channel B, and having a similarity score between these two messages. Of course, it should be high enough to be chosen, and getting the time difference between these messages and putting them into that function. Similarity is an exponential function with exponential decay in order to like the more message is similar between them and the less time passed from their publication, the more influence is one channel to another one. So counting within any messages of this count of these channels, we have an influence score, like how a channel A influenced on channel B by time, and etc. So here's an example represented as a graph, and like we are filtering, and we discount we reveal that here are two almost groups that influence between them. So it's ReRU, RT Russian, BB breaks, etc. So here how they retranslate their messages between them. Another factor is based on the previous one, which took in account the time and time difference and the gap and the similarity score of the text, and creating the cascade, like identifying the root message that start, and then after that we are calculating all similar messages that precede that messages. For example, there wasn't a message in a real like in at 3:28 p.m. and in 4 minutes the same message in Ukrainian with almost the same meaning but a bit rewritten. It was published in Ukrainian channel to the Ukrainian audience. The question is how that message was translated from Russian to Ukrainian channels. So as we told, we have an integration model. So, but all factors for now have different forms and the dimension. So starting from the first one, it's of course it's okay. It's in the depth zone of 0 to 1. But the next one is not absolute values, which should be normalized with min-max normalizations over that entire corpus. And the next one is we have a few graphs, and using the Jacquard measurement to count the numbers of graphs where two channels meet in them and how they interact in the same networks over the time. So the final integral model looks like that. We have three functions that are integrated with weighted each one, where of course weights in sum should be 1. It should and when all three factors say as 1, it of course it should be their integral score equal to 1. So the advantages and limitations of the model, so actually it incorporate the factors of different dimensions, allowing us to see different factors from the same text by emotions, etc. Time. Another advantage is to its scalability. We can add another factor to that model and it be more comprehensive. But there are some limitations. Actually, the weights are set empirically, and there is no approach to still not approach to tune them. And actually, adding a new factor require the changing the values of those weights, of course. So actually, to get that values, of course, we need some processing, some system. So there was a system under the hood where took the data, process them, store them, and represent. So this system is balanced. Every step is logged and is completely stateful. So it could start the processing from the middle of their path. And if data is versioned, stored in order to compute a more advantage and aggregated values in the future. So actually, there was an final example how we have an integrated model with weights like 0.44, 0.42, and cascade with 0.1 and represent us like 4 clusters of channels. Here we have below the Russian channels, which communicate between them, and they have a high correlation between them. At the top, we have the intersection of Russian channels with pro-Russian pseudo-Ukrainian channels like Stranaiway, 112, and more resident. So also display us some interaction between them, yeah. In that corner, we see some self interaction between pro-Russian or pseudo-Ukrainian channels. And of course, at the center, there's a group of Ukrainian-oriented channels that have their own policy. It does not interact with the Russian and the pro-pseudo-Ukrainian channels, yeah. So conclusion, so we have proposed an integrated model that combine few dimensions. It compare messages and sources by time, semantic, and network relatively. So there's a proposed information system that is automated to calculate them, and the future work is to refine and tune existing methods, plus adding a sentiment analysis factor with using like some BERT family model. That's it for now. Thanks. Any questions?
Thank you, Artem. Colleagues, maybe have a question? Okay, no question. I have one question. Please say, what is your main advantages of your solution?
The main advantages actually is I think the autonomy, because it's a huge pipeline that could grab the data almost in real time. Yeah, some delay, but it took the data, analyze them, store them, and integrate in the final result on demand on the real data. And we are asking, for example, the Q4 of a previous year, so we have data for that period itself, and it is useful to identify group of channels that interact between them. Especially, it's useful for OSINT OSINTers, yeah.
Okay, thank you.
Yeah, you're welcome.
Maybe someone have a question? No. Okay, thank you, Artem. So the next and finish report will be an adaptive stabilization framework for resilient information system under dynamic and unvirtual conditions. The speaker will be Timur Isayev. One moment.
Good afternoon, dear colleagues. Can you hear me?
Yes, we can. Please
Okay.
share your presentation in presentation mode.
Yes, one moment. Okay.
Please.
So I'm here to present our work and adaptive stabilization framework for resilient information systems under dynamic and adversarial conditions. So let's start. Why is it important and relevant? Modern information systems operate in different environments. Fundamentally different from those for which they were originally designed. Workload characteristics, timing patterns, and structural data properties evolve continuously, even during the normal operation. The situation becomes significantly more severe when fake events, timestamps, manipulations, and coordinated multi-stream disruptions are introduced as part of the cyber attacks. Why static systems fail? Systems relying on fixed threshold or static analytical models become unstable under dynamic conditions. They generate excessive false alarms, fail to detect emerging threats, and cannot maintain consistent performance when data properties change unpredictably. Key limitations of current approaches. Signature-based and rule-driven approaches do not evolve over time. Machine learning models require repeated retraining whenever data distribution shifts, losing effectiveness rapidly. Hybrid and heuristic methods offer improved flexibility but typically lack a mechanism ensuring long-term stability. And adaptive systems can react to anomalies but cannot maintain consistent performance under evolving data conditions. These challenges indicate that solutions must adapt across multiple layers of information systems, not only identifying deviations but also analyzing their consequences and regulating internal parameters within the closed feedback loop. So, framework architecture and our framework architecture and mathematical foundation. The adaptive framework is represented as a discrete mathematical system whose behavior evolves over time. At each discrete time steps t in the system receives new information, processes it through harmonization, evaluates the deviations, adjusts internal parameters, updates analytical models when necessary, and decides whenever the new configuration improves stability or must be rolled back, forming a closed feedback loop. Stage 1. System state sigma t. Sigma t equals h of t, theta of t, m of t, where h of t is the harmonized representation of all incoming data streams. Theta of t is the internal parameter vector controlling thresholds, weights, and sensitivity coefficients. And m of t is an analytical model for detection and classification. Stage 2. Harmonization mapping, h of t. H of t equals h x of t theta of t. Heterogeneous streams xs of t are transformed into undefined internal representations hs of t through normalization, scaling, trust weighting, and smoothing. A deviation ds of t equals hs of t minus rs is computed against baseline rs, then normalized into lead indicators that s equals phi s dst theta t. Stage 3, global impact and parameter adaptation. Each stream is assigned importance weight vs. Global impact I of t equals sigma s ws multiplied by zs of t quantifies overall destabilization influence. Parameters update via theta t plus 1 equals a theta of t and I of t, bounded within safe limits. The system becomes more responsive when instability increases and more conservative when conditions stabilize. And stage 4, model update and stabilization. A tentative model m-t is generated and compared with m of t via consistency score 0 to 1. If sufficiency high, the new model is accepted. Otherwise, the previous model is retained. A stability index evaluates whether the adaptation improved system stability. If not, the system rolls back to sigma t, preventing harmful adaptation from propagating. Okay, let's look through our architecture more visually. There's three-module closed-loop design. The adaptive stabilization framework is structured as a discrete system whose behavior evolves over time according to interactions between data streams, internal parameters, and analytical models. At each time step, the system receives new information, processes it through harmonization, evaluates deviations, adjusts internal parameters, updates analytical models when necessary, and decides whether the new configuration improves stability or must be rolled back. The architecture consists of three vertical models: data harmonization and deviation detection, transforms raw heterogeneous streams into normalized deviation annotated representations, parameter adaptation and control, interprets and drift indicators and updates internal thresholds and weights, and model update and consistency generates tentative model updates, validates them against the current model, and triggers rollback if stability does not improve. Component interaction sequence. The interaction sequence diagram represents the discrete operators as message passing through interaction between 6 system components. The data source sends raw observation to harmonizer, which applies timestamps normalization and schema alignment, producing harmonized values forward to the detector. Key component roles. Data source ingests raw energy streams, network flows, log entries, behavior metrics. Harmonizer applies normalization, scaling, trust weighting, and smoothing to produce unified internal representations. Detector compares harmonized values against reference baselines and computes normalized drift indicators. Adapter aggregates drift indicators using importance weights, producing a global impact value and updating parameters. Model update generates tentative model updates and compares them with the current model with consistency scoring, and stabilizer computes the recovery index and sends the final accepted rollback signal closing the feedback loop. The stabilizer's final acceptance of rollback signal influences the next iteration of harmonization, deviation detection, and parameter adaptation. This feedback loop is what distinguishes the framework from open adaptive system. Every decision is validated against the stability matrix before being measured and preventing harmful adaptation from propagating. So after we look through our architecture, it's time for the experimental setup, datasets, and test bed. The experimental evaluation was conducted to assess the framework's effectiveness under dynamic, noisy, and adversarial conditions. All experiments were executed on a workstation equipped with the 16-core processor, 64 gigs of RAM, NVIDIA RTX 4090 GPU, 2 TB NVMe SSD, with Windows 11 Pro and using Python 3.13. This is 2017 datasets, contains 2.8 million flows, 2.2 million normal, and 500,000 malicious, used as the primary real-world benchmark for detection performance evaluation under adversarial conditions. Synthetic drift stream consists of 1.2 million samples with controlled drift, noise bursts, and adversarial manipulations, designed to simulate realistic adversarial conditions, including gradual drift, abrupt changes, timestamp manipulations, and overload attacks. And 5 core evaluation metrics: stability index, recovery time, adaptation, overshoot, model consistency score, and detection performance. Types of drift used in testing. Drift is a change in statistical properties of data over time, meaning the system's normal behavior slowly or suddenly stops matching what the model was originally trained on. When drift occurs, models become less accurate, thresholds lose relevance, and detection logic begins to fail unless the system adapts. Gradual drift. Gradual drift refers to slow, continuous changes in the statistical properties in common data over time. It simulates realistic operational environments where user behavior, network traffic, or system workloads evolve naturally. Key characteristics: distribution shifts happen smoothly, no sudden anomalies, models integrate progressively, requires long-term adaptation rather than emergency correction. Abrupt drift. Abrupt drift represents sudden large changes in data distribution. This type of drift is common during system recognition, sudden workload spikes, or unexpected operational changes. Key characteristics: and distribution changes instantly, not gradually, causes immediate model degradation, requires fast stabilization and parameter correction, and tests the system ability to recover from shocks. Adversarial drift is caused by intentional manipulations designed to mislead or destabilize the system. This includes time-step manipulation, noise burst, fake events, coordinated multi-stream attacks, and other hostile actions. Key characteristics: changes are malicious, not natural, often multi-vector and coordinated, designed to bypass detection or overload the system. Test resilience under hostile conditions. So results: stability index and recovery time. The stability index quantifies the system's ability to maintain consistent analytical behavior under disturbances, normalized between 0 and 1, where higher values indicates more stable operation. The proposed stabilization mechanism significantly improved SI across all scenarios. Recovery time measures how quickly the system returns to a stable state after a deviation. The proposed method reduced recovery time substantially across all tested conditions. Under adversarial manipulations, the most destabilizing scenario, SI improved by 0.3, demonstrating that the system consistently maintains higher stability even under severe dynamic changes. On average, the system restored stability more than 3 times faster compared to the unsupplied baseline. And under adversarial disturbances, recovery was 3.6 times faster, reducing recovery time from 4,120 milliseconds to just 1,130 milliseconds. Adaptation overshoot and model consistency score. Adaptation overshoot reflects the magnitude of excessive parameter adjustments during adaptation. Lower values indicates more controlled and precise adaptation. The model consistency score evaluates whether the updated model preserves the analytical behavior of the model before adaptation, capturing how similar the model's outputs and decision tendencies remain across a representative evaluation set before and after update. The proposed system reduced a adaptation overshoot by approximately 65% across all scenarios, confirming that the stabilization mechanism prevents harmful overcorrections and maintains controlled adaptation dynamics. Model consistency score under adversarial manipulation, MCS improved from 0.49 to 0.82, the most dramatic improvement among all scenarios. This indicates that the stabilization mechanism successfully counteracts manipulations, restoring the model to a reliable and predictive operational state. Across all 3 scenarios, improvements in MCS confirms the framework updates the model effectively by preserving analytical coherence. Detection performance was assessed using accuracy and false positive rate. Accuracy reflects the proportion of traffic flows classified correctly, while FPR captures how often traffic is incorrectly flagged as malicious and critical metric in intrusive detection systems because elevated false positive levels lead to unnecessary alerts, operator fatigue, and reduced trust in systems outputs. When drift was introduced without stabilization, accuracy dropped to 87.5%, and FPR increased to 9.3%, demonstrating clear degradation. With the proposed stabilization mechanism enabled, accuracy increased to 96.1%, while FPR decreased to 3.1%, confirming that the framework enhances real-world detection performance by reducing false alarms and maintaining high classification precisions. So summary of key achievements: plus 34% detection accuracy compared to static and semi-adaptive baselines under adversarial conditions, 68 to 82% fewer false positives, reduction in false positive rates across test scenarios, 3 to 5% degradation under drift, minimal performance loss on the distributional drift conditions, and 82 to 95,000 events per second, high throughput with 3 times faster recovery from attack-induced distortions. Conclusion and future directions. The proposed adaptive stabilization framework successfully guarantees reliable analysis under drift, noise bursts, and adversarial environments. By unifying harmonization, deviation detection, adaptive parameter control, model consistency checks, and closed-loop stabilization in a single pipeline. The framework achieved 30% boost in stability under extreme drift, a threefold reduction in recovery time, 70% reduction in adaptation overshoot, and strong model consistency even under high distributional drift. Current limitations. The heuristic policy approach restricts exploitation of long-term temporal dependencies important for highly volatile data streams. The framework assumes drift events are independent, but real-world scenarios frequently involve correlated or cascading disturbances. Assessments concentrated on network construction detection, wider validation in financial, industrial, and IoT domains is needed. Future research interactions, predictive drift trajectory modeling instead of reactive adaptation, time-related attention mechanisms and sequence-aware meta learning for proactive parameter adjustments, adaptive policies evolving based on historical recovery patterns, extension to distributed and multi-node environments for coordinated stabilization, and explainability-driven stabilization providing interpretable justifications for adaptation decisions. That's all from me. Thank you for my attention.
Thank you, Timur. Dear colleagues, any questions? Okay, I have a question. What is the main limitation of your approach?
The main limitation is it currently developed to work on only one computer systems. In future work, we will be working with that so this framework will work on multiple computers, even big clusters of them, and even on some supercomputers. So for now, we need to change our parameters so the framework will work on multiple computers at the same time.
Okay, thank you for your answer. Colleagues, more questions? No? Okay, so thank you for your report. Please close your presentation. Okay, colleagues, let's move on. And now we are going to the workshop close ceremony. Actually, we have prepared a set of certificates, yes, and we'll send the link of uploaded certificate all participants who made report today. And we would like to make give award certificate to Artem Kalancha, as he submitted the best paper and made the best report. Applause. And we have prepared another certificate, the most active participant, Andrei Nichiporuk. Applause. As well, we have prepared set of certificates for speakers. They look like this one. So we will send you later. And dear colleagues, I'd like to say that the 7th International Workshop is come to the end. I'd like to express my sincere gratitude to everyone who has contributed to making this event a success. Workshop brought together researchers from different countries, exchange ideas, present innovative results, strengthen international scientific cooperation in the field of intelligent information technologies and information security. Today we have witnessed screening presentations, engaging discussion, and the exchange available experience. Every presentation, question, and discussion has contributed to advancing our shared scientific goals. New collaborations have begun. Existing partnerships have grown strong, and fresh ideas have emerged that will undoubtedly lead to future research achievements. I'd like to extend my deepest appreciation to our keynote speakers, authors, session chairs, reviewers, members of International Program Committee and Organizer Committee. Your professionalism, dedication, and hard work made this workshop possible. A special vote of thanks goes to our international participants. Your willingness to collaborate with Ukrainian scientists is deeply appreciated and demonstrates that science continues to unite people across the world, even in difficult times. Holding an international scientific event in Ukraine together carries special meaning. Despite the challenges our country faces, we continue to teach, conduct research, innovate, and cooperate with colleagues around the world. This is possible thanks to courage and sacrifice of Ukrainian armed force, who defend our country every day. We are profoundly grateful to them for making it possible for us to continue our scientific work and international cooperation. On behalf of organizing committee, I sincerely thank each of you for your participation, your excellent contributions, and your commitment to advancing science. We look forward to welcoming you again at the next IntelITSIS workshop. Thank you for being with us. Now our workshop officially closed. Thank you and see you again next year. Colleagues, maybe somebody would like to talk, make a short speech. Ulhan?
Thank you so much. I would also like to say a few words of gratitude to all the colleagues, participants, and guests. Also, on behalf of our organizing committee, I would like to thank everyone for taking part in our scientific workshop. We are grateful to all speakers for their interesting presentations, for their valuable research results, and active contribution. Your achievements have made this event meaningful, productive, and inspiring. We hope that this workshop will encourage your further scientific cooperation, new idea, and future joint projects, and hope to see you all in a year. So thank you so much for participating. Stay safe and take care.
Thank you, Olhan. Okay, colleagues. Maybe somebody wants to say something? No? So thank you. See you next year. Bye-bye.
Thank you.
Thank you. Bye-bye.